Welcome, folks. We'll give everybody just a second to join in, and then we can get started. So, welcome everybody. My name is Matt Bauman, and I'll be leading today's training. I want to hear just a little bit about how yesterday went, where you all ended up, and if there are things that we want to review from yesterday before we dig in. We can allow folks to start jumping in allow folks to come back and log in. But while we're waiting, let's hear a little bit about yesterday and see how things went and where we can go. Where we should start today, and if there are things we should go over again.
Thanks, Matt. Can you hear me? This is Amit.
Yes, hi.
Yeah, hi. So yesterday, I think it was a great session. So we started off with like very basic introduction to machine learning and deep learning. So we went through the concept, and I was very glad to see some good examples, like in Google, you say apple and oranges. We have seen those enough examples. So I'm glad to see that we took a different kind of approach, and how we jump into an image and like trying to figure it out, how to extract the feature. So that was the starting point. And then we covered basic topics and how to do the machine learning in manual way, like how you create gradient descent functions, derivatives, etc. So that was nice to see, how the manual is very good to see when the things work, how actually they work, right?
Yes.
And then later part of the session, what we did, we tried to use Flux. So I think the whole objective is Flux provides you all this information, the ready-made bundle, everything all together, so you don't end up writing complex gradient descent or loss functions manually. So
exactly.
Yeah, maybe the last part I would ask you if you can repeat that. I understood but just like how the Flux. What is the idea behind Flux? Okay, how the neurons. So actually, yesterday I asked a question: what is a single neuron? Okay, what does it actually do? I understand neuron is a tiny little computation, but overall big picture, how the neuron fits into this whole Flux ML neural network thing, right? What it contributes. So it's good to understand how the single transformation works, but how does this fit into the big picture? So
it's just like the perfect introduction to today's course, and amazing summary. I couldn't have said it better myself. So yes, today's lectures will all focus on Flux, and whereas yesterday was really focused on the concepts, today is focusing on the tools. But it sounds like some additional bridging of the gap there would be really beneficial in terms of how what the things in Flux represent and how you bring it back to those basic concepts.
Right.
So yeah, that's perfect. We can definitely talk about that. I want to hold off in answering your questions there because I think I'll try to literate throughout the remainder of the lectures and talk about how those things look and the way in which that works. But yeah, we'll see how that goes. Any other comments or requests or complaints or things that went well, things that went poorly, things that you're still struggling with that we can potentially spend a little bit of time here at the beginning getting folks all on the same page? And of course, if you're not familiar using your microphone, you can always just use the chat, and I'll try to keep the chat screen up on my computer to make sure that we are, yeah. If as I'm typing through things, I encourage and very much enjoy interruptions and diversions and digressions. That's one of the beautiful things about doing this interactively and in an interactive environment is that we can stop and take a detour and look down an alleyway or something along those lines to see what's happening and how to better understand it.
So sorry, I'm still waiting for other people. If anyone else want to chime in and have any feedback.
Yeah, sometimes I feel like you need to wait a little bit of an awkward time to get folks comfortable with speaking or jumping in. But we'll just wait a minute or two longer here, and then we'll dig into the lectures.
Sure. So while we're waiting, sorry, I have one more follow-up question. So,
absolutely.
I think most of us, including myself, we are coming from different backgrounds, like PyTorch or Tensor. So sometimes, like, do you recommend us to undo that learning, or can we just go and still use that part of it, like some part of it?
No, absolutely. I wouldn't suggest undoing that learning at all. In fact, the basic concepts are all the same. It's just kind of how we spell it is a little differently. And I think that it'll put you in good stead. And in fact, Julia does have bindings to all of those packages as well. And so we're using Flux in this course. That's Julia's native machine learning toolbox. But there are bindings to TensorFlow, PyTorch, and things like that that allow you to use the skills that you know. Now, of course, you're going to get the same performance. You're going to have the same functionality. You're just calling it from a different language. That can be beneficial sometimes if the rest of your tool chain is in Julia, for example, or if there are other parts that work better in Julia. But I like Flux because it's the pure Julia solution that kind of takes a slightly different approach to it, because of it kind of all comes down to the way in which we take gradients, right? So when you did your manual stochastic gradient descent function yesterday, you used that numeric gradient thing where you added a little bit of distance from your current points and evaluated the function twice, right? And then saw how far away you were, did the division, normalizing and getting that set. That's how we did the gradient, in the first days of this course. And so that is a terrible way of taking derivatives. It's really nice because it's easy to code, right? And it's very visual because you can, look at the graph of seeing how that works. In fact, why don't I just share my screen here already, and we can start talking about this a little bit more concretely. Right. So yesterday you wrote that stochastic gradient descent function, right, where we went in and let's see, I think it was probably like this notebook maybe, where you had to, write your gradient functions and put them together. Where is that? Maybe it was this one. Yeah, here we go. So, where you went through and added that point and, figured out, got your loss functions. And then here, this is what I was looking for, where you, added the partial derivatives, right? And you had the partial for all of the parameters of your neural network here. And in this case, we just had two parameters, right? There is the W parameter, the W vector with 2 data points, and the the B offset, you can think of it as. And this is really just a linear regression at its heart. When you only have one layer here, it's really just doing a simple regression. It's done so in a complicated way, but that's the way it works. And so when we evaluated this, right, we evaluated the loss function at our given data point, and then our loss function at our given data point with the parameters shifted a little bit. This was how we got our let me pull up the chat just to make sure. Yeah, okay. And this is how we got our gradients here. And so to get our gradients for all three of these guys, for all of our parameters here, so that way we can write our stochastic gradient descent function, we actually needed to call into our model 6 times, right? There are 6 function calls into the loss, and that loss function is what calls into our model. That model is what evaluates the neural network, and then that's how we find the gradient with respect to all of these guys. And so that's a lot of overhead here. And really the game in a lot of machine learning tasks is eliminating as much overhead and finding the gradient as is possible. So the way that other toolboxes do that is that they tend to, you express your computation in the form of a highly structured graph, where you explicitly say, what your layers are and things like that. You name them out. You have to kind of do this, it's almost like meta programming, right? Where you're programming and telling the system how you're programming, right? Where you're kind of saying what the layers are. And that's kind of the standard for programming against TensorFlow, right? Where you need to explicitly label all these things. The reason for that is so that way it can take shortcuts in its gradient computations. That's why you're creating that computational graph. That's why you're doing that. And so that's one of the things that Julia does differently, is that because Julia is itself a fast enough language to be implemented in itself, it allows you to do some really cool compiler techniques where we can actually ask the compiler itself to generate the gradients. And in that way, you don't need to have a program, create a program to create your machine learning model. Instead, you just write your machine learning model and the program is the definition. And Julia can ask the compiler, hey, compiler, can you give me the gradient version of this function? And it's rather remarkable that you can do that. If there are if statements, those become discontinuities. If there's other things, it just passes them along. It's kind of tricky, but it all comes down to the chain rule from calculus. And so by doing that, we can kind of write our algorithms a little bit more succinctly and straightforwardly than you might have been used to doing coming from other tools. And so that's where we're going to go today, is kind of seeing how Flux works, seeing the tools that it provides and gets us going there. So hopefully, it sounded like you made it through, defining your own neuron to learn and got you the stochastic gradient descent function up and running. So today, let's dive in, and I'm going to open up notebook 13 just to start here. I don't know, were you able to peek inside of Flux at all yesterday and use Flux?
Well, I just looked into this file. So unfortunately, for some reason, if I compile Flux, it's giving error in my machine, and something wrong with that.
If you copy paste it into the chat, you might be able to identify it quickly. There's a handful of common issues there that might be easy enough to solve out. So what I did here is, to add Flux, right? You ask the package manager to add to the package. You just simply say add Flux like this. It'll go out, download it, add it, and make it available to you. And then you can say using Flux. It'll take about 5 minutes the very first time you do this. And then things should be much simpler. Oh, interesting. I see. That one is new to me, the error that Amit posted in chat. One of the things you might try is just simply updating all your packages. So if you just type in up at the package prompt here, so just as a reminder to get into the package prompt, you type that left square bracket and then just type up. And that will upgrade all the packages. Just make sure that you're on the latest versions. Sometimes that can fix problems. You know, if folks have found that problem in the past before, looks like my hunch is that that's well, I know that it's related to the GPU capabilities of Flux there. It's trying to load some GPU libraries, which should be available, but I'm not quite sure why that's having trouble. So
yeah, maybe it's a Windows machine. Actually, it's my, I don't even have admin rights on my machine. So something to do with that. Yeah, we can fix that.
Yeah. Shoot. Okay. Everybody else able to add Flux to their package and type using Flux at the command prompt here to bring in the package and hopefully automate a lot of what we did yesterday. All right. So the first thing that you'll find in Flux is, and one thing to note here, if you've not discovered this yet, there's a way in VS Code here to turn on soft wrap. And let's see, how do I, here, toggle word wrap. If you go to the view menu and toggle word wrap, it'll make all these comments actually fit on your screen, which is a lot nicer because a lot of them are very long. There's a shortcut that's, I think, Alt-Z maybe, or Option-Z if you're on a Mac, that just does that. And so then you can see these things. So inside, when you say using Flux, it brings lots of tools that you can use and work with, including some of the basics of machine learning that you talked about yesterday. Like one of the things that you used the entire time yesterday was that sigma function, right? That function that did the sigmoid transform and that is already predefined for you here. It uses the Greek character sigma, which you can type just by simply typing \sigma and then hitting the tab key here. So hitting tab will change that over to sigma. And if in general, if you ever come across some Unicode character in Julia that you don't know how to use, you can just copy and paste it into the help prompt down here. And it will tell you how to type it. And then if there's help actually defined on it, it'll tell you what that object does. And in this case, it's doing that definition that we repeat over and over and over again throughout all the notebooks to define the sigmoid function, because it's a common, what's called an activation function to compress your domain to be between 0 and 1 and give you uniform output between them. So that's why it was a nice model function when you were doing just a simple two classification problem where you were just looking at the difference between an apple and a banana, for example, right? Because it could tell you, zeros are apples, ones are bananas. So we can use that to create a dense neural network here, right? And this is, oops, I didn't want to do that. I hit Shift Enter, which will execute the entire script. I just want to do Control Enter, which will send this this line of code down here. So this dense function here does, it creates a dense neural network with 2 inputs, 1 output, and a given activation function. So how does this thing work, right? We understand how to build a simple SGD from yesterday, but now we have this fancy model object. What does it do and how does it work? Well, if there are 2 inputs, maybe we can just evaluate it at 2 values, right? And see what happens and see what we get out. We get a single value out, right? So that makes sense. we have a model here that takes in a vector with 2 data points as a part of that vector, and gives us a single answer back. So what did it do to compute that answer? Well, it used the definition of that neural network. And what is that? Well, remember we used things like W and B in defining it, right? In defining what our output of our model was, it was 1 over exp of what is that sigmoid definition here? 1 plus exp of negative x, right? 1 over 1 plus exp of negative x. But that's not all we did, right? What we did was we did some transformation with those w's and b's, right? Where we did w times x plus b like this, right? Yeah, let's yeah, I think yeah, I think like that will work. I'm trying to get this right. So that's the way that we did this in the past, right? We had our W's and our B's and got that going. Of course, we don't have W's and B's here defined, right? We've just defined a model itself, but the model itself contains a W and it contains a B, right? It automatically defines these things for us to give us the standard structure of a neural network. Now, when we did this yesterday, or when you did this yesterday, the W's you used was a simple vector. In Flux, it's arranged as a matrix, as a single row of a matrix. And all that means is that instead of doing a dot product, right? Because before what you did for between W and X here wasn't a multiplication, but it was a dot product. You took 1 divided by U, dot or C dot like this, right? You took the linear algebra dot product between W and X is kind of how you did it, or maybe you used the dot function from within linear algebra, right? So that is the way in which that worked before. If you're going to use that dot function, you needed to bring in linear algebra like this, right? But if our W's are set up as a matrix instead of a vector, well, the dot product is simply a matrix multiplication between a column and a row. And so that means that we can take this, our X. So let's define X as being 0.2 comma 0.3, like I had evaluated my model at, right? So the model evaluated at X is this value here. So what is created here? What are we doing? Well, what we're doing is we're evaluating 1 over 1 plus exp of negative W times X, and now it's just the model dot W times X, right? Where we do that matrix vector multiplication plus B like this. Oh, and the B is also encapsulated in our model, right? And I goofed here because I think I'm going to have a problem where, yep, I'm trying to raise, I need to do this pointwise and the division pointwise as well. Yeah, I need to. Yeah. Sorry about this. There we go. So here I've defined, this is exactly what we did yesterday, right? The only difference is that instead of using a dot product, I'm using a multiplication here. I'm adding a few extra broadcasting dots, and that's just a small niggle to get things working. So because we're not getting a scalar element, we're getting a 1 element array back. But that's exactly the same as what we see when we evaluate the model at X here, right? This is exactly the same answer. The only difference is, we're promoting just slightly differently, so we get a little bit more precision when we did it this way. But Flux is being a little bit conservative in, using lower precision arithmetic here, because that scales extraordinarily well on GPUs, and so that's why it only uses the slightly lower precision. And in practice in machine learning, that is a great trade-off to make. And so this is what Flux does and what it bundles up for you here. So that's the core fundamentals here of building models in Flux, is that all you're doing is you're creating some function, right? This model thing, we can look at it. It's a dense network that contains some fields that is callable, and you can treat it like a function. So that is the core understanding here. The beautiful thing here is that it encapsulates all of our parameters, as well as this activation function directly in here. So we have our model.w, our model.b, and so on and so forth. Peter asks a good question about even lower precision floating point numbers. So 64s are the default floating point numbers. That means they have 64 bits of precision, which translates to roughly about 14 or 15 decimal digits. If you go down to float 32, then you are down to about 7 decimal digits, and 7, maybe 8 decimal digits of precision. And you can see that just in how they print out, right? Julia will print out essentially the shortest number of digits possible that will give you the same answer. So here we're getting 6 digits, here we're printing out 6 digits. So yeah, 6 or 7 digits of precision is what you can see with float 32s. So then if you were to just kind of naively shrink things down to float 16s, we're talking about very, very limited precision, right? We're talking about 3 decimal digits of precision. And think about that in scientific notation. You're almost at the level of only caring about orders of magnitude at this point, right? And so they're a little tricky. The other thing that makes lower floating point representation smaller than 32-bit tricky is that there's not very good hardware support for it. And the hardware support that there is a little idiosyncratic. There are different competing definitions for what exactly a 16-bit floating point number looks like. There's some trade-offs you can make in terms of the range of numbers that it can evaluate versus the number of significant digits that it has. And so different systems take that differently. The short answer is that yes, you can use float 16s in Julia, and it'll just happily create them and represent them nicely. It prints them out with the explicit float 16 here. But they're not as certain to give you a reliable speed up, simply because it all depends on the hardware you're using. So that's the way it works. But yes, they work great with Flux. It's just whether your hardware has the definitions for them appropriately. You can, one of the beautiful things about Julia in general is that it's really easy to create new numeric types. And so we actually have not only the float 16s available to us, but there's also another B float 16 as a competing implementation of float 16. And there's a package that'll implement this for you and be fast on Google's hardware. So Google has hardware that works efficiently with this particular floating point format. Both of these will work just fine with Flux. Like the capabilities are fine. They know how to add, divide. It's just that sometimes if you're not on an optimized hardware, then Julia needs to emulate those operations instead of coding down to the efficient native things. So yes, Peter is on top of things. Google's hardware that I'm talking about is TPUs. TPU stands for tensor processing units. And that is where, it's kind of the next iteration of a GPU. It's geared towards tensor computations and specifically matrix-matrix multiplications, which are really what's at the heart of machine learning. And so, yes, Julia actually runs on TPUs. It's one of the 2 languages that does, along with TensorFlow, and their kind of idiosyncratic back end. It's a little tricky to get set up, partly because, using TPUs in general is a little tricky. But yes, it is possible. All right, so let's see where we are in our notebook here. So we've gone over, those weights and those biases. We've talked about the type of our model, and we've talked a little bit, about. So we managed to reproduce its output, right? We figured out what's happening behind the scenes. We've kind of pulled back the curtain on what happens when you evaluate the model at a given data point and figured out how to reproduce its output. Now, what we'd want to do though is, we want to evaluate its output, but we also need to ask it what the gradients are of that function, right? And so this is where I was starting to talk at the beginning of today about how gradients are really what underpins the core of any machine learning implementation. And in Julia, you can take the gradient of potentially an arbitrary Julia expression. So here, let's take the gradient. So let's define this function f that's a simple polynomial expression that takes in an argument x, squares it, multiplies it by 3, adds 2x plus 1, right? And so we can take the derivative of this. And if you remember from calculus, the way you do this is just with the chain rule, right? You first see that you're squaring it, so the 2 drops down, you subtract 1, so then this becomes 6x is the gradient here, plus 2, right? That's going to be the gradient with respect to x. And we can do this ourselves, right? We can just define partial, why didn't that work? Partial, tab, there you go. Partial f of x like this is just going to be defined as 6x plus 2, right? That's the calculus transform here that's equivalent. And you could do this by hand, but we don't want to do this by hand. And we're already telling Julia what all the operations are here, right? In this case, it's very simple. It's all straightforward math. So as long as Julia knows how to take the gradient with respect to exponentiation, with respect to addition, with respect to multiplication, and knows how to chain them all together, that's just the chain rule from calculus, well, then it can compute this for us directly. And if I ask for the gradient of f with respect to its input at the x equals 4 here, it will, go through there. It takes a minute, just to compile all of the architecture needed for computing gradients here. But you can see here that I get an answer of 26 back. And if I were to, call into this partial of f at 4, if I define it first, and call into my manual thing, right, I get the same answer. So that's good. My knowledge of calculus, while rusty, still survives basic differentiation. So that works just fine. And in fact, I can even ask Julia not just to evaluate the gradient of f with respect to x at a given data point, I can ask it for this generic function itself. I can say, hey, given this particular evaluation, can I have that function that defines it? And so that is available to you. I think let's see here. Yeah, if I do, so there's a operation called pullback where I can do the same thing that gives me a partial, a function effectively that I can evaluate that will give me the derivative. And in fact, it puts it in here really nicely that it tells me exactly what that's going to be. And so that is the core here of what's going on, is that we can ask Julia to compute these things. Same thing if there are 2 arguments, right? If there are 2 arguments, I can do the same sort of thing. And it does it simultaneously, first with respect to the first argument, then with respect to the second argument. And what it's doing here is the partials, right? And so it's, first doing x holding y constant, and then changing y and holding x constant, and giving us those values the same way as it did before. So all of these things just work. They happily coexist. They happily work with how things, how Julia works. But now when we want to talk about the gradient of our model, what do we really want here, right? When we want to compute, right? So where are we going to go with this in our machine learning framework? If we're going to define a new machine learning task, a new machine learning pipeline, and instead of doing this all ad hoc, we want to lean on these gradients. We want to lean on Flux to define these things for us. How do we ask Julia for the gradients there? Well, first of all, we need a loss function, right? We need some way of evaluating a loss with respect to some data points, right? So I don't know. So we have my data point X. Let's just say that the output here should be should be 0, just to give me some label that I can play with here, right? Just to kind of play with incrementally. So we know that model of X should be equal to 0, right? That's the ground truth. We're not close to that. And so the way we optimize our model, right, is by constructing a loss function. Given a particular model at a data point and a known ground truth, you just ask how far away are you from this? And how do you do that? Well, the way you do that is you evaluate your model at your given data point, right? You just call your model function at it, and you subtract out your y. And well, often you want to do the mean, the absolute difference here, right? If I just subtract them, that's not going to give me a distance. You would want to do like an absolute distance, or really, a very, very common one is the square distance, right? And if I had many data points, this would all come together and I could do like a mean squared error kind of thing, right? And that's exactly what this loss function does. So I want to evaluate this loss function with respect to my model at X against Y, right? And see what those things are. Oops, where did I mess up here? Oh, I need to define this in terms of, so remember what I get out of my model here? When I evaluate my model at X, I don't get a scalar, I don't get a pure Julia floating point number, I actually get a vector. And for right now, this is going to be a little annoying for us that we get a vector back. But in a few lectures, you'll see why this exists and why this happens this way. And so to deal with this vector, well, we just need to, so we evaluate our model at this X data point. What we get back is a vector. So if we do pointwise arithmetic here, we can subtract y from all the elements in our vector. Well, we only have one element in our vector, so that's just going to do the one thing, and then square all the elements in that vector. So these dots here add, they're what's doing broadcasting or pointwise arithmetic, and it's essentially saying, let's ignore this array for right now. Since it's just a one element array, let's pretend like it's a single element. So now let's evaluate our loss again. So we have our loss at our model, given X and Y, we get some value, right? Some value greater than 0. And the goal here now will be to minimize that, right? We want to get the gradients of this loss function and then update our parameters and iterate, right? That's kind of how the structure here goes. So think about this, right? The things that I've shown you how to do here so far are a little bit different than this general structure, right? What I've shown you how to do is, given some function f like this, f of x and y, you can see this pure math definition of how you make this work. I want to, evaluate, I want to get the gradient of my model. When I got the gradient of f, right, remember how I did that? I got the gradient of f with respect to x and y, and I got their gradients back. And it was very easy, very simple, very straightforward. And I was taking the gradient with respect to the arguments of f itself, right? So, f of x, take the partial with respect to x, you compute it through, get that going. Y, same deal, all those partials. And that's straightforward, that's the calculus that we know. So if I wanted to do the same thing here, and I wanted to do gradient of, well, the function that I want to take the gradient of is the loss function, and I want to evaluate that loss function at a given model and at my data point and at my Y. But I don't want the gradients of these things, right? I don't want to take the gradient with respect to the model. Who knows? How would you even do that, right? Like that's not a very sensible operation here. Taking the gradient with respect to the input, well, that'd be telling me how I can change my input to make my model match the output better. That's not what I want to do, right? I don't want to change my input. I can't change my input. That's the ground truth that's coming to me. That's the data that I'm getting in. I can't change my data to fit my model. It's a little backwards. Similarly, I don't want to take the derivative with respect to Y either. That'd be saying that I want to change my label in order to make my model match my data better. In other words, I want to change what I've already assigned, what I've already gone through the work of figuring out what the output should be here. Let's change that to make it match the gibberish model that we started with. So none of those things are what we want here, right? We don't want to take the gradient with respect to a function. We don't want to take the gradient with respect to our inputs. We don't want to take the gradient with respect to our outputs. And in fact, if I try to do this, I'm sure I'll get some crazy error that's, hey, I don't even know how to take a gradient with respect to this. So what do we do then? How do we get this set up to work? Well, the answer here is simply to, say, well, let's look at the gradient of our loss. But really all we want to do here is we want to look at the gradient of some arbitrary function that takes no arguments, that already has all of its arguments pre-populated, where we pass in our model, our X and our Y, and get out that first element out of it, right? Remember that our loss is going to spit out an array. We just want to get a single element back out. And what do we want to take it with respect to? Well, we want to take it with respect to the parameters of our model. Now that's a little bit of magic that I've not shown you how to do yet. So the params of our model here, it simply spits out model.w and model.b. So here you can see we have our 2-element array, and our W's are like 0.15, -1, sure enough, and 0. So the parameters of our model, essentially our model has taught Flux what parameters it has, what it can change, what gradients, what are the tunable things inside of it. And it spits it out in kind of this generic architecture that you can kind of imagine it putting anything there, right? And the key thing is that it's just identifying what you want to take the derivative with respect to. So that means that when I evaluate this function here, so remember, this is our loss function, right? And if I just evaluate it right away, it gives me a 1-element array. I can get that single answer out to give me a single scalar loss value that I want to take the gradient with respect to. So when I write this magical syntax thing here, what it's doing is it's creating an anonymous function with 0 arguments. And on func like this. And if I called that, it will evaluate my loss function, right? It does just this. It's the same thing. The only thing that's magical here is that I'm kind of deferring its computation a little bit. I'm putting it into a function so that way, when I ask Julia for the gradient, it can evaluate this, and then it can go in and do its magic with respect to the parameters of the model. Now we get back out something that's a little funny. I'm going to call it G's here, and it's this grads object. And, if I look at it, it's just spitting me back out. So I got some sort of gradients, right? What did I get back out here, and how do I know how to use it? Well, this is a little bit of a magical data structure here that allows me to ask, what the gradient with respect to my model.w was, and what the gradient with respect to my model.b was. So this G's object here has some special indexing defined on it that says, hey, when you index into it with some value, and if I tried to do this with some other value, it'll say, hey, I can't differentiate that. Or if I tried to do some arbitrary thing, it'll say, hey, I didn't take the derivative with respect to this thing that you just passed me. So you can only get out the derivatives of the parameters of the model that we passed in, but that's perfect, right? This is kind of the general structure that we have. So Alberto asks a question that I'll pause to answer here. So differentiation is algorithmic, and you can differentiate symbolically. And there are some algebraic simplifications that can happen if you do that. And how is Flux doing this, right? Is it doing symbolic differentiation, or is it doing something different? And the answer is that it's not quite symbolic differentiation. It's kind of doing a mix of forward mode and backward mode, kind of depending upon the argument types, using very specialized kernels for arrays and things. And essentially it's able to see the structure, the entire structure of your program, right? It knows how to compute the loss, and therefore it knows how to compute the derivative of the loss. And it's one of these things that kind of blows your mind when you think about it. Like, how can you take the derivative of an arbitrary computer program? And my analogy here is that, well, if you really think down to the core of what a processor does, right? The processor in your computer really just does arithmetic and moving data around. That's all it knows how to do. And between those two things, it's able to create really complicated things to the point where you can seamlessly hear my voice, see my face, we can play with these things, you can see it on the screen. All of that is kind of this behavior that's coming out of a very, very, very simple basic layer. And so in the exact same way, we have this very simple basic layer of algebra and arithmetic that we can differentiate. And even with if statements and things like that, you just add discontinuities and you always differentiate it with respect to exact values, so you know which branch you were in and things like that. So then you can get the derivatives that way and apply the chain rule backwards. And as you're applying the chain rule, well, the code that Julia is creating can be optimized, right? And it is in fact optimized by LLVM, and it can take advantage of some of those things. And so there are times at which a purely symbolic differentiation would give you a really nice closed form solution. There are other times when a purely symbolic differentiation would give you a horrible rat's nest that would be far more complicated and far more convoluted to actually evaluate than just running the program itself. So it's kind of this interesting in-between of automatic differentiation where it's not doing symbolics, it's not doing numerics, it's just doing the compute in essence. So yeah, it's a really good question that kind of takes some time to wrap your head around, and really the subset of compiler programmers who can work on this system is very limited. I've not fully dug into this aspect here yet, but it's pretty cool. The end story, though, is that now we have our gradients of our model with respect to these things. And that means that I can update these guys, right? And so just like last time where you defined a learning rate, often, called ADA, say, define that as 0.1. Well, we can update our model.w just by subtracting out ADA times the grads with respect to our model.w, right? We're just going to subtract away the gradient, do our gradient descent, scale it by some learning factor, and this will update our w such that hopefully we get closer to the ground truth. And same thing with model.b. We can do exactly the same thing, ADA times g's of model.b like this. And that updates it in place as well. And now if we evaluate our model with respect to x, hopefully we're a little bit closer than where we were before to what we had wanted. And so that's the architecture that Flux provides. Hopefully this all looks very familiar from yesterday, right? Where we just talked about gradients, stochastic gradient descent is just the matter of iteratively doing this step, right? Iteratively grabbing the loss, taking the gradients and iterating. And you just go through all the data points in your data set like that. So with that, we're getting towards the top of the hour. Let me just make sure there's nothing else here. Yeah, I've taken this opportunity to dive ahead a little bit, so that way we'll be in really good shape in our next notebook. We won't need to go over some of these basic concepts quite as thoroughly. But hopefully this lays the framework now for today, where we'll dive deep into Flux and use this basic paradigm to get a lot done. So there's all sorts of really helpful functionality. So for example, I defined my my loss function manually, right? When I did this, I did loss of that to be, this. Well, I could just also have used flux.mse of our model at x and our y like this, right? And do exactly the same thing. And that'll give me the mean squared error and potentially across many data points at that point. So that is Flux, and it's kind of this toolkit, you can think of it, of all the building blocks in order that you need in order to build your neural networks. So with that, let's take our first 10-minute break here. When I run this course, I don't know how Daria ran it with you yesterday, but the way that I like running this is around the top of every hour, I'll take a 10-minute break, and where you can stretch your legs, grab a snack, grab some coffee, and we'll come back. And the way I like doing this is just pulling up a Google 10-minute timer, because I don't have it's like the easiest timer that I have access to is just a Google search. But I'll keep this on my screen. I'll reset it here so you have a true 10 minutes and see you back here somewhere around 3 or 4 past the hour. All right. Welcome back, everyone. While we were away, Peter asked about some speed comparisons between Flux and other systems. I don't know. Yeah, I'll look for them during our next break. I was grabbing some food during this one, but I'll see what I can find. The key speed differences that you'll see are indeed in training the neural networks. And a lot of that simply comes down to how you're doing, how you're structuring the gradients and how you're doing your matrix multiplications. And so in some ways, there's almost it depends upon the structure of your neural network. But generally, Flux is on par with those, sometimes, maybe a factor of 2 behind, which really is quite remarkable considering the amount of engineering infrastructure that's dedicated to those systems. Now, what you gain out of that, though, is the flexibility of definition, the flexibility of execution. It's really easy to move to the GPU. And then once you move to a GPU, it's a whole different ballgame at that point. Of course, TensorFlow and PyTorch can also be run on GPUs. But the beautiful thing here is that you can embed arbitrary Julia functions. And it's a lot easier to define your own neural networks, to define your own things. And importantly, there's a new field coming out now where we're able to embed neural networks inside of much larger algorithms. And again, because they're just functions, right? Like what I was showing in the previous lecture, Flux neural networks are just pure Julia functions that allow you to evaluate the code and ask for the derivatives. And so that means that you can do what's being considered now a new form of scientific machine learning, of just having very, very small machine learning networks instead of very large ones embedded within a larger system. And it can be a part of a differential equation. It can be part of some iterative simulation. It doesn't matter. It's just a function. And so there's some really, really cool functionality there. And what it means is that you don't need near as large or near as deep a neural network to encapsulate the behavior, because you're just taking a small aspect of it. And so, TensorFlow and PyTorch, they're not dumb. They're not doing anything dumb at all. They're extraordinarily skilled programmers and can often exploit the computer just as well as it can be. And we try to match that. In many cases we can, especially the well-trodden neural network styles. But there are cases where I've seen Flux to be 2 times slower, but that in general we tend to be very competitive. So I'll see if I can find some examples there. It's something that we're continuing to iterate on and work on. But yeah. Any other questions from the first lecture, or before we move on? Then let's jump to notebook 14. So let's start by, oh shoot, I think I'm missing CSV and data frames. So let's start by loading in some data, right? And whereas in the last lecture, you talked a lot about what an image looks like, what things are, and how the image is structured and how you extract features out of that structure and how you do it. Well, in this lecture, we're just going to, and moving forward for the rest of today, we're going to start from a pre-existing delimited file that has the features extracted for us. I think you might have used this in your last example yesterday. Is that right? These apples and bananas CSV tab separated files here. Is familiar to you, or should I talk a little bit about the data frames here? Cool. So then you're familiar with, how these data frames look, how they work. Each column is a different feature that we've already done the image processing for you and gotten out your metrics from. So subtracting out the background, what's the height and width of your image, kind of ignoring the white space, I guess. And then the mean red, green, and blue. And so yesterday, a lot of the course was looking at like the mean green and the mean blue amounts, right? Because you found that the mean red wasn't very informative. Something along those lines. So yes, the mean amounts here. So these are kind of features that have already been extracted. We have 492 examples from apples, and we have 490 examples from bananas. And really, as a machine learning person, unfortunately, the sad truth is that a vast majority of your job is spent building this cleaned version of your data, right? This kind of first step is called extract, transform, and load, where you go from the messy real world situation down to a very nice, concise tabular format that has all your features, all your examples already enumerated, ready to go for you. So that is, how we do, get these things out. What we want, though, is not a table of features, but we want a single data points, right? Single examples for each row that has the values that we're after. So we're going to use the red and green values out as our two inputs to our model. We're going to be creating two input model, one output, right, with a 0 or 1, whether we're an apple or a banana. And this is just going to, be using those techniques that we talked about last lecture, bring them together in a real world example. So now we have our apples and our bananas. We just want to stack those together, right? So that way we have 982 examples. The first bunch are apples, the second bunch are bananas. We're going to do the same thing with our labels, right? Where we just say, however many apples there are, fill zeros in for them. However many bananas there are, fill ones in for them. Give ourselves our set of labels. And now we have our data and our labels already formatted for us to use with Flux, right? So we load in Flux. How do we build our model, right? So we really just need, I'm going to do this all right here incrementally and make this pretty short. Hopefully we can get through this example pretty quickly, but we want to create a model, right, that we can call. And we did this already in last hour. Dense neural network, 2 inputs, 1 output, and let's use that sigma activation function, right? Easy enough. So that's our model. And all we need to do now is call our model. We have X's, right, as our list of inputs. We call our model with respect to our X's like this. We can, set this up. We can call it against all of them. So hopefully this model of our first element of our X's is going to be the same as the first element of our Y's. It's not, it's pretty far away. So how do we do that? Well, we change the parameters of our model in order to match it. And what we would have done in the previous lecture was, manually taken the gradient of, well, we need a loss function, right? Loss of X comma Y will give us our flux.mse of our model evaluated at X against our Y, right? And that will, compute our loss for us. So that can be our loss function here. In this case, I'm kind of simplifying things by passing my model as a global variable. And most Julia code, this would be very poor for performance, but in machine learning code, so much of your time is spent in gradients and training that this doesn't matter. It's kind of one of those funny things where, in traditional Julia code, this would be considered what's called type unstable, but here we don't need to worry about it because it's not a big problem. And kind of one of those magic things about optimizations is, you don't worry about them unless they're a problem. And so we don't need to worry about this case, but I'm just pointing this out to you, and that, if you're working with Julia, it's something to look out for. In this case, not a problem. All right, so we have our model, we have our loss. What do we want to do here? Well, we want to do a stochastic gradient descent, right? Or do some sort of gradient descent. We could manually define that, but the whole point of using Flux is to have that defined for us ourselves. And in fact, Flux has built into it a descent optimizer, is what it's called. And if you ask for help here, you can actually see that it does exactly what I did before, right? It takes all parameters, iterates over them all, and just simply runs, updates that parameter, subtract out some learning rate, eta, like we're familiar with from literature and before, times the partial of that parameter. And we know how to get the partial, right? By asking for the gradient, we just asked Julia, what's the gradient with respect to the parameters of our model? So we can just say, hey, we're going to use a descent optimizer. And the kind of standard idiom here to use is just to call this our opt as a descent. And we can use the default learning rate here. You can see it's documented to be 0.1. That's just going to be the default value there. So we have our model, we have our loss function, we have our optimizer. Now what? Well, now we need to train our model, right? And that's going to do that iterative looping over all of our data. We want to, what do we need to pass in order to train our model, right? So hopefully there's going to be some train function that we can use that Flux hopefully will provide for us. What do we need to pass in? Well, your first gut instinct might be, well, we want to train our model. So you might think we want to pass in our model. But think about what we need in order to do this. We don't actually use our model. What we do is we call our loss function, right? And we pass in our loss function in order to train this. And we'll evaluate our loss function at our data points. Then what do we need? Well, we need to pass in all of our X's and our Y's, right, in order to make this work. And I guess, Matt went through the trouble of creating this opt thing that says descent. It's like how we're going to do this optimization. Probably should pass that in too, right? So that's kind of the general structure you would think or hope to have here. And indeed, there is a train function. But in fitting with Julia's idioms here, it's not just train, it's flux.train exclamation mark. So in this particular case, this is a function that you need to use qualified. The authors of Flux decided, hey, I want to make it explicit that you're training a Flux model here. And I think they did this so that way, this is a common word used throughout machine learning. So that way it's not, you can actually cooperate nicely with a bunch of machine learning packages. And sure enough, here we go. So what do we need? We need our loss, oh, that's what I was forgetting. The parameters of our model that we want to take the gradients with respect to, right? We need to know when we take our gradients of our loss, what the parameters are. And I can simply say, hey, let's grab the params of our model. And those are the things that I'm going to take the gradients with respect to. So loss we got, oh, we should change this to be flux.train, right? That's what we found it to be here. So the loss we have matched the params. We know how to get those out of our model. But then the third argument here is simply called data. And what I had hoped to use was my X's and Y's. I have all my X's together, all my Y's together, and Flux just wants a huge chunk of all my data together. And what it does is it just calls loss of each data point for data of that data point. So since my loss function takes in my X label or my X data and my Y label, I want to structure my loss function such that my X's and Y's are not a vector of all my X's and a vector of all my Y's, but rather I want them to be, tuples right back to back. And the way you can do this in Julia is with a nifty little function called zip, X's and Y's. And by default, it gives you back out a bunch of gibberish that just says, yep, here's a zip, which isn't very helpful, right? It's just looks exactly like what I just wrote, except the vectors are written out here. In order to actually see what this thing's doing, we can collect it, and that will bring it all into an array. Essentially, this is a lazy structure that generates its elements on the fly. And in order to see what the elements are that it generates, well, we can just call collect and it'll put them in. And so you can see here that it's taking my first X's data point, X's of 1 here. Let's make this a little bigger so we can see. So my first X's of data point is 0.5, 0.2. Sure enough, 0.5, 0.2. And my first label is a 0, right? That's because it's an apple. And so this is just kind of destructuring all my X's and all my Y's to zip them together. It's a very evocative imagery here, right? You can imagine a zipper, taking each element and putting them next to each other and going up along the way, just like a zipper does. So that's what we want to pass in as our data here, is all of our X's and our Y's. And now what this will do is it will simply, iteratively walk through all my X's and alongside all my Y's, right? They're zipped together, so that way they happen simultaneously. Ask for the loss with respect to the params of the model, get the gradient of the loss. It doesn't actually call the loss itself, it just asks for the gradient thereof. It doesn't need to know the value of the loss. In fact, it just needs to know the gradient because all we care about is the slope. And then, does it with respect to our optimizer. So let's just see what happens here. So you have our model of just take a canary in a coal mine. That first X's value, right, is going to be 0.35, and I want it to be 0, right? And so I can run this. And this will do a gradient descent over all my X's, all my Y's, and get them going. I can go back to see, okay, did I improve my model? No, I actually made it significantly worse with respect to this one data point. And one of the reasons why that's happening is because, well, remember my data here is all of my X's in order, and it's just going to iterate through them. So that means that my model, as I train it, I'm just going to iterate through a whole slew of examples where the answer is 0. And then I'm going to iterate through a whole slew of examples where the answer is 1. And so that's going to mean that, well, pretty much all of my outputs here after training this one loop are going to be 1. And if I look at, say, the last example of my X's here, indeed, it's also almost 1. And that's doing the right thing here, right? It is actually training my bananas to look like bananas, but it's also training my apples to look like bananas, because the last 500 or so examples that our training loop saw here were bananas. And so it's learning and thinking, well, everything's a banana, if you'll pardon the anthropomorphization. So how do we fix this? Well, the answer is, well, remember, this is just a descent algorithm. What you did yesterday was a stochastic gradient descent. What's the randomness there? Well, the randomness is in shuffling up all of our X's, right? And so using the random standard library, there's a shuffle bang function that you can use that'll just take all the elements in a vector and shuffle them up. And so we can use this to shuffle up the collected zip of all of my data here. And now, oh, oops, what did I do wrong? That sure looks right. Oh, I think I had something selected here, funny, or if you only have a subset of your VS Code thing selected, I think it'll only execute that selection. So I think where I erred was I had some funny subset selected, so it gave me a strange error there. But yes, this does work, right? And each time I execute this, it's iterating through and doing another iteration over all of my X's and all of my Y's. So let's see if I'm doing any better with my canary in the coal mine here, model of X's of 1. Hopefully it's not near 1 anymore. Sure enough, it's getting closer to 0 again, right? And so now we're bringing our model back together. Hopefully our last data point is still somewhere high, and sure enough, it is. So those two canaries in the coal mine are looking okay. How would we visualize this or look at this in general? And there, let's see, do I want to do that now? Yeah, sure, let's do that. So the notebook here, this notebook will walk you through this solution here. And does a lot of the things that I did in the last notebook. I kind of like front loading a lot of this architectural details about how Flux works in the previous lecture. So that way in this lecture, we can just kind of see how it all comes together. If you're still curious about any of that, the remainder of this lecture will go through this much more closely and have nice text and answers and things for you to look at. Talking about things like why we're a row of a matrix, for example, nicely noted for you here. What I want to jump down to here though is let's see. Oh shucks, the graph is, I think the graph is in my solutions folder. Oh wait, I am in my solutions folder, aren't I? Yeah, I am. Yeah, I think, well, we'll look at this a little bit later on. There's some nice ways of visualizing this. I guess we can just do it quickly here, incrementally or interactively. Where was I here? So right, this was my algorithm here. We can bring in plots, right, using plots. And that'll take a minute or so to compile if you've not used it yet in your session. You'll want to add it, of course, too. This is something that has gotten significantly better over the past year and a half and is even better yet on the upcoming 1.6. But what I want to do here is I want to plot all of my X's versus all of my Y's, right? Or well, let's do it a little bit more simply here. Let's scatter these guys. So put a scatter plot where all my X's and all my Y's are this, and we'll group them by their label. And actually, I want to scatter plot all of my first elements of my X's against all of my last elements of my X's, done pointwise again, right? So if you do the pointwise, so remember my vector of X's has all of my data, and each data point has two values, right? The mean red amount and the mean green amount. And so if I get the first element out of all of those data points, well, then I'm getting essentially the mean green amount on my X label. So let's do that. X label is mean, I think red is the first one, red amount. And Y label is the mean green amount. I'll just call it mean green and mean red. And let's see if that gives me what I want. So that's going to scatter these guys. So I'm grouping them by their labels. So I should end up with two groups, one for apples, one for bananas, and get our first element out of each one and see where we are. There we go. So now we have a nice plot here that has our mean red and our mean green of our two examples. And you can see Remember, zeros should be our apples, ones should be our bananas. And now what I want to do is I want to find the dividing line, right, where my model says everything, you know, or what the values are here for my model. And there's several ways of doing that. One is to just say, okay, my values span from, so yeah, let's see, we have, we can just evaluate the model, right, at all of these points, and put together a contour plot around those data points. And I think actually, if I just do, let's see if I can do this, contour of our model, and yeah, I think 0.4, 0.6, and 0.1, 0.6, 0.55 maybe. See if that works. Yeah, I was afraid of that. What is this? This what I want to do. Oh, let's see here. Yeah, I guess I'll just do it this way. So my x's here, I'm just going to define as 0.4 by 0.01 to 0.65. My y's I'll define as 0.1 by 0.01 to 0.55. Okay, and then now I can contour x's versus my y's, and my model evaluated at x's and y's like this. Let's see if that works. Oh man. Rays cannot be broadcast. Oh, right. I need to put my y's on another dimension. Maybe. Oh, right. Oh, that's annoying. We'll do it like this. Model of x comma y. Oh, right. It needs to be a vector, right? That's the answer. So what I was missing here, so what I'm doing is I'm creating a grid of my model that I want to just visualize what the values of my model are, right? And I don't want an array of arrays. I want to get out that single element that my model is going to spit back like this, right? So I'm evaluating my model at the grid of my plot here. And so now I can contour this using this definition here like this. And I'll copy paste this into the chat for you all following along at home. Oh no. Do I have my x's and my y's backwards? I might. There we go. All right, that is the definition I want. Let's pull up my x's again, put that in my file here, so I can plot this out nicely. So those are that's kind of just the grid that I'm going to use here. There's some fancier ways of doing this. This is just kind of my quick ad hoc example. So contour, and I'll use a contour bang to add my contour to the scatter plot that I first create. So let's evaluate all of that all at once, maybe. And pull up my plot here. And you can see now the values that I get. And I'm getting, a gradient here, kind of, you can imagine a slope of my sigma curve, where 0.5 is this reddish value here. And sure enough, that divides this really nicely, right? That contour level divides our values really nicely and easily, gets that going nicely. And in fact, maybe I can do this a little bit simpler here. Now that I contour, I'm just curious if I, no, it's not quite right either. Okay. Yeah, I'm not sure what I'm doing on here. That's all right. The definition that I have is just fine. I was just fighting with the contour plotting syntax is all. And there are other ways of doing this, and we have other fancier plots that we'll go into a little bit later on. But this just gives you an idea of what this model is doing and what's happening here. And we can train this some more, right? And hopefully make this curve a little bit sharper. So that way, you know, when we're down here, we're a little bit more certain than being 0.4, for example. And so sure enough, just by executing our training loop a number of times again and again and again, well, we'll keep doing that, right? And you know, hopefully our loss function will continue to decrease, and more importantly, our plot will continue to sharpen. And sure enough, if I go back and forth here between, you know, this was what it was before here, and now our curve is getting sharper, right? The contour lines are closer together in the middle and farther apart at the end here. That's exactly what's happening, as our model is sharpening its view into the trained data set, right? And so now if you get a new data point, right, and you can imagine having a test data set now where you would have new data points that you would want to, you know, put some new data points here, 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 you know, something like this. You can imagine some more data points coming in and seeing what the model would give you versus, you know, some new orange guys coming in here. So test data is very important. It's kind of how you need to work in order to validate your models and make sure that you're not overtraining to your the data that you already have. But that's the way that this works, and that's what's going on here. So with that, we are ready to, oh, oops, I need to clear my annotations. Don't want those dots following me around. Okay, so that's notebook 14, right? And the key understanding here is that we don't need to manually do any of the things that we did yesterday. We just define the structure of our model, use it as a function, put it in a loss function, define how we're going to optimize its parameters, and then we train those parameters, taking the gradients with respect to this of the loss function across some data set. And if we want to do a stochastic gradient descent, well, we want to shuffle that data set around so that way we're not training all zeros and all ones. There's no structure or bias that will incur when we finish our training. So that's the basics of Flux. Let's move on to notebook 15 now, where we're going to start talking about neural networks, right? We've talked about what a single neuron is. It's just simply that matrix multiplication and a output, right? We just have the single output and getting things, you know, going and making that work. Let's see, I think actually to do this might be simpler to pull this up in. So the text here references these things. I still need to figure out a better way of embedding images within Julia text files for these examples. What I want to do here is I'm just going to go into my training here, and we have our kind of the way in which these things are going to work. So great, that's right. So this is the first image that we have, right? So imagine if you didn't want to just train against apples and bananas, right? If you didn't have, because we have only been talking about apples and bananas so far, we've been able to have a single model output, right? Where that single model output was either a 0 or a 1, depending upon whether it was an apple or a banana. And it was very simple and easy to work with, simple to understand. We had a nice structure to our model, and it made us, using that sigmoid activation function, make a lot of sense, right? Because we were clamping our outputs between 0 and 1. We had meanings to 0 and 1. It allowed our neural networks to do what we wanted them to do. What we want to talk about here, though, is the capability of, adding, say you have grapes. How would you add grapes to this example, right? Well, you could take that one single output and make it a 2, right? So then you say, okay, bananas are 0s, apples are 1s, grapes are 2s. But then you can no longer use a sigmoid activation function, right? Remember, that's limited between 0 and 1. And it adds this kind of weird point where the apple is somewhere in between a grape and a banana. Why should an apple be on some spectrum between bananas and grapes? That doesn't make sense. And so the general structure we want to use is what's called one-hot vectors. And that is where we simply say, let's, instead of only having one output of our model, let's have 3 outputs of our model, where we have, the first output here as saying, is it an apple, right? It's essentially, asking, are these things apples or are they something else? That's this first output here. The second output is asking, are they bananas, right? It's simply saying, hey, if the model is a banana, put output 1, otherwise output 0. Same thing with grapes, right? If the output is 1, it's a grape, otherwise it's 0. So in this way, our model has 3 outputs. Every time we evaluate our model, we're going to get 3 answers. And our 3 answers are essentially answering the questions, is it an apple, is it a banana, or is it a grape? And in that manner, you can kind of extensively work with many hundreds or thousands of classes, right? Because you just simply increase the number of outputs, and each output is just looking for one particular thing. And this is a very common idiom, very standard way of looking at things, and gets us to the point of talking about a whole neural network. Let me clear my screen again. So that is the way this works. And then we want to kind of extend this out by, repeating our model with different weights, right? We could potentially have lots and lots and lots of models, right? In order to have 3 outputs, you could simply define 3 models. You'd have model 1, model 2, model 3. You do the sigmoid calculation, w.x's plus b's, all those things, where each model has its own set of b's, each model has its own set of w's, and so on and so forth. All of these equations are the same, except for which w's and b's it's using, right? And in fact, if you highlight them, you'll see all the commonalities. You can see, it's almost exactly identical, except for, which w's you're using and which b's you're using. So how could you do this in a different way? Well, this is where the beauty of linear algebra really shines, right? Where instead of taking the dot product between all of our w's and x's, taking that dot product many times, right? And here, this particular example, you'd have 3 different dot products, right? One for the weights of an apple, one for the weights of a banana, one for the weights of the grape, and take that dot product 3 times. add your different B's, your B's for your apples, B's for your bananas, and so on and so forth. So you'd have one of these things for each one. Well, this is why Flux uses, instead of a vector for its W's, it uses a matrix for its W's. And this all just kind of comes down to the linear algebra that backs all of this up, is that the dot product between two vectors, that's exactly what happens with matrix-matrix multiplication and matrix-vector multiplication. If I have a matrix here, let's just kind of define a matrix M as being, say, 1, 2, 3, say 10, 20, 30, and 100, 200, 300 like this. So I have this matrix that's structured with, 110, 100, 220, 200, 330, 300. And if I were to multiply this by, let's see, what numbers should I use here? Let's use a vector. Actually, yeah, let's add one more row here. Let's make it not square. We'll make it a little bit more obvious. So I have my matrix. I want to multiply my matrix by a vector of 3 values. So let's do M times 0.4, 0.5, 0.6 like this. And what that does is it is multiplying all of the, so 0.4 times 1, 2, 3, 0.5 times 10, 20, 30, I'm sorry, let me start over. It's taking the dot product of my first row by this vector. And so what that means is I'm taking 0.4 times 1, 0.5 times 2, and 0.6 times 3, and that's the answer that I get down here, right? And you can see that 0.4 plus 0.5 times 2 plus 0.6 times 3, times 3, and that's the answer that I get, right? That's the dot product of the row against a vector. And same thing happens here and here and here. And you can imagine this as being 4 separate dot products, right? We have 4 separate dot products and we get all 4 answers all tied together in a single array. And so now you can see why Flux puts its W weights if there's only one output in a row, right? The number of rows of my weights here determines how many outputs I'll get at the end. And so this is how you can structure your matrices now. And this is why matrix-matrix multiplication becomes such in the fore here, is because there's been lots and lots of optimizations, many decades worth of optimizations going into making these things fast, and significantly faster than doing the individual thing, right? Doing these things individually. And so you can take your single matrix, multiply it by a single vector, and get 4 simultaneous answers instead of taking 4 separate vectors and dotting them. That's the only magic that happens here. And so when we create, for example, if I created a new model in Flux that was a dense neural network that took 3 inputs and 4 outputs, well, what's the shape of that W going to be? It's going to be 4 by 3. It's going to be that same shape that I just played with in the toy example up there, where we have 4 rows, right? Those 4 rows determine our output vectors, and 3 columns. Those 3 columns determine our, they're like, they line up with the number of inputs that we have and the number of data points within a single example, the number of elements within a single example data point. So that is, how we can have multiple outputs. And so, for example, if I wanted to extend my apples and bananas example to have still stick with 2 inputs, but now support 3 outputs. I want to do model equals dense of 2, 3, right? Then I can define model at any data point, right? 0.2, 0.3 like this, and it'll give me 3 answers. I should have used a sigmoid transformation still. Right. So it'll give me 3 answers. This one is my, the you can kind of start thinking of it as maybe a probability or a certainty that it's an apple, a certainty that it's a banana, a certainty that it's a grape. And we're getting all three of those answers simultaneously. And since all three of those weights are separate, right, they're all in that model.w, but now my model.w has, well, I guess here, let's do model.w. Now my model.w has 6 values. And so if I take my gradient with respect to this, I'll get 6 answers in that array as well, right? I do the same thing. I'll get 6 gradients and 6 things simultaneously. And this is now where we start thinking about, why it's so important to be smart in how we take our gradients, right? You don't want to evaluate my model, what would it be, like 12 times in order to get all of the gradients, holding one of them constant at a time. If I did the numeric differentiation, that would be computationally intractable once you get to larger models. So this is, again, talking to that gradient sort of structure. Okay, so that's kind of the intro here. The core understanding that I want you to get out of Notebook 15 is simply that, we're writing a single model that is answering 3 questions simultaneously, right? And we're doing so by leaning on linear algebra to express our problem now not as a dot product, not as a row of a matrix times a vector, but rather as a whole matrix times a vector. And that matrix vector multiplication is more efficient than doing the 3 things separately. Any questions on this point? Looks like I lost my chat window here.
Hey, Matt, I'm still a little lost about that. So this model is predicting 3 different outputs, right?
Right.
How does it relate to that, hot vector? So for example, like, how do I know which one is which?
Right. So it's entirely based upon how I train this model, right? It's going to try to match the labels that I give it. And so my labels for my apple now, what is the label of an apple going to be? It's not going to be a single value anymore, right? It's not going to be a single 0 or a 1, right? Remember, in the last session, I created my y's as a vertical concatenation of zeros of the size of my apples and 1's the size of my bananas, right? And this was my labels. What will my labels be for this new model, right? That's answering 3 questions at a given time. Well, it's going to have 3 answers, right? And so my answer for my apples is no longer going to be a single 0. It's going to be, say, a 1 0 0, pretending that the first answer here is that first answer of my my apples. My bananas then are going to be 0 1 0, right? That's going to be the ground truth of how many bananas. And then the same thing with my grapes, right? I'll have a 0 0 1 here for maybe 2 grapes. So here you can see all my apples, all my bananas, and then I have 2 grapes apparently in this data set. So each y now has multiple elements as well. And so then when I compare, right, compare the output of my model at this given data point, I'll compare it against these 3 things, right? So I'll compare that against my y's, and how would I want to do that? Well, let's take the mean squared error of it, right? MSE between that of y's of 1, and that will give me, how far away is this output from what I would really want it to be. And here we're using mean squared error because it's not just a single data point anymore. It's 3 data points that I want to all simultaneously, drive this first one to be a 1 and the second 2 to be 0. Does that answer your question? That's a really good question.
Yeah, definitely it does. So in a real world, so for example, hypothetically, in a classification problem, I have like, tens or hundreds of different fruits, right? So I would create that, that's a recommended way, or there's an alternate approach?
So it kind of depends on what you're trying to classify. This is actually a common problem that is kind of a fun extension of some of the things that we'll talk about. There's a really cool data set, in fact, called let me open up my browser here. The Fashion MNIST data set that does exactly this, that gives you a whole bunch of examples of different things that you would want to classify. So for example, shirts versus pants versus shoes versus blouses versus purses, things like this. And so you can classify all of these things. And maybe if I can make this bigger, you can see all the different examples. They're just lots of images that you can classify and use as an example data set here. We won't use this in today's lecture, but well, maybe we could poke at it a little bit. It could be fun. But the idea here is that you would, in this example, you would have as many classes as there are rough categories of things that you want to categorize. So, you know, maybe you'd have shirts, pants, women's shirts, women's pants, or women's dresses, shoes, you know, maybe about 5 different things, purses, 6 different things here that you'd want to classify, and you'd have 6 different outputs for your model then. And then the labels for each would be a what's called that one hot vector, where there's only a single one and all others are 0. Does that help make that a little bit more concrete?
Yeah, it does. So, you know, maybe I'll ask a follow-up question, a silly question. Yeah. So actually, it's a real world problem. So for example, I'm doing some, so in Amazon, okay, there are 5,000 different type of things, catalog. So in the real world, should I go for, like, you know, making a hot vector for 5,000, or it's not even a good idea? Like, I should do something else, right?
I would try for a coarser representation. It kind of depends on what you're trying to get, right? Like, are you trying to get all 5,000 of those categories exactly right? Or are there, you know, higher level categories that you can target? And kind of a 2-stage model actually can be very powerful in this manner, where you would first categorize things from, you know, clothing against electronics, for example, against hardware tools, right? Okay. So you'd have like very, very coarse categories, and then you might have a specific model that just, you know, gives you, is it a screw, is it a drill, is it a screwdriver, you know, the specific examples within that. It can kind of help keep your models at a more tractable size, and can, you know, allows your first model to give you that more coarse representation, of which you have lots of examples, and then you can do specialized training where you're only looking at, you know, the parts that you really care about, and perhaps you don't care about, you know, hardware at all, and all you really want to look at is clothing. Well, then you could, you know, categorize everything at those course levels, but then throw everything else out and then do a smaller thing on just the clothing or something along those lines.
Okay, thank you.
Yeah. Yeah, so this is such an important concept, right? And you don't really want to be creating all of these vectors, especially if they're going to be thousands long, which they can be, right? There's nothing wrong with that. And in fact, we can show you an example where there's a 1,000 element long example built into Flux to look at a little bit later on. But this is actually storing 8 elements in memory. And we can do better than that with Julia, is that, you know, we know all of these things are 0 except for, say, the 6th element. We can represent that with a Flux one hot vector type. It's like a very specific vector that simply says, hey, the 6th element is hot out of 8 possibilities. And so you just simply say which element is hot and what the possibility indexes are. So 1 through 8 are my indices. I errored initially here because I simply put an 8 here, and 6 is not one of those potential labels. So you can say the 6th element out of my labels 1 through 8, and it'll just automatically do that for me here. And this is represented extraordinarily efficiently with just 2 values, where you just store the 6, you just store the 8, and you don't need to store all 8 elements. And this, of course, then translates to many hundreds of thousands of elements, right? Where you can say, oh, whoops, I guess not quite that many, where you can say the 6th element out of, I don't know how many is that, 100 million elements is hot. And it doesn't need to generate all of those elements in memory. It can do them on the fly lazily. So we'll be working with this in the next lecture to build up one of these multiple output models. With that, let's take our 10-minute break and we can come back and look at what it looks like to do a multiple output model. I will pull up my timer again and see you at, it's gonna be about exactly 10 past the hour.
All right. Welcome back, everyone. Let's dive into our next lecture. So that was notebook 15. We'll move on to notebook 16 so let's do it on here. Notebook 16 on doing that single layer network that has multiple outputs. We'll do exactly the same thing that we did before, right? Where we will load in data frames. Let's do a few more examples than what we had done before. So we have 3 data frames of apples. We'll concatenate them all together to give us, a few more examples, about 1,500 examples of apples. Same exact structure as what we used before. Let's do the same sort of thing here, right? You can, pull out those X's like we had done before. Exact same idea. This time, for no real good reason, we'll use the red and the blue values instead of the red and the green. Same idea, just something different, a little bit different in this notebook. Then we'll do the same thing here with our, so let's do it this way, give ourselves a bit more screen real estate. Same thing with our bananas. In this case, we'll just still only have 1 data frame there, so 490, and 3 examples of grapes. And note that all 3 of these classes have different numbers of rows, and that's totally fine. You might have to, in extreme cases, be a little bit careful about how you, work with lots of different, if your examples are wildly unbalanced, because then your model is going to see lots more examples from one class than another. And so you may want to do subsampling in order to even out your classes if you have wildly different numbers of examples. But that's, in general, it's not that big of a deal as long as you're within, a factor of 2 or 3 or so. It's not too major. You just don't want it to be, constantly training against one class and not seeing the others when it's doing its gradient descent. So like we had talked about before, we have our X's. Again, it's just 2 element, a vector of 2 element vectors. So we're just gonna have 2 inputs, but now we have 3 classes, so we'll have 3 categories. And so we'll do exactly what we did before using these one-hot vectors. And I'll just do them right here. Let's just do this entire data frame, this entire solution in one go. So our Y's are going to be the same idea, right? We just want to do VCAT. But what do we want? We want to fill one hot, flux.one hot, where the first one is hot out of 3 examples, the size of our apples, right? And then same thing here, do the exact same idea. Let's just copy and paste. Only now size of our bananas. Structured correctly. Okay. Oh, and I'm missing a parentheses here. That's why it's not tab indenting nicely for me. So there's my my bananas. I want to change which index is hot to be the second one, and do the same thing for my grapes. Close that parentheses, close my VCAT, and there we go. So now we have my one hot, oops, this wants to be a 3, right? So I'll have a bunch of labels. The first bunch are going to be my apples. So the first output is going to be true, right? It is an apple, not a banana, not a grape. My last bunch are going to be grapes. It's going to be 0, 0, 1, not an apple, not a banana, but it is a grape. And in the middle are going to be my 0, 1, 0s. So those are my Y's. Now, what do I want to do? Well, I want to, why don't I just go back here to not this notebook. You can save it, sure. Let's go back to notebook. I can't see with this. It's hiding behind my my control panel. Oh, I can grab that and drag it. Nice. There we go. So not that one. Oh, did I close it already? Shucks, I must have closed. Oh, here it is. There we go. So this is what we did before, right? These 4 lines of code was our model and how we got things going. So let's just copy and paste that and see how we have to change it for 3 outputs. So we have our model, right? We want to instead have 2 inputs, but we want to have 3 outputs now, right? So you have 2 inputs, 3 outputs. Our loss function, well, that can stay the same, right? It's the MSE of our X against our Y. And because we're using that flux.msc, it works just as well for a 1 element vector. Remember, that's what the output was before, because we just had a one output, so it's a 1 element vector. Now it's going to be a 3 element vector, and you get the mean squared error of those 3 outputs against the 3 values in our single label of our 1-hot label. Our optimizer can be the same. Our training set, that can be the same too, right? We can just have that all be exactly the same. And this even is exactly the same. We have our X's and our Y's in the same structure. We can do exactly that same thing where we set this up. I'm going to make this just a little bit simpler. So let's call this data and say data is that. So just kind of split that apart. So I guess now it's 5 lines of code, right? Oops. So 5 lines of code, our model, our loss function, our optimizer, the data, and we train. And that's it. So let's define all these guys. And to quantify this, right, to gain an understanding of this, what I had been doing before, right, was looking at canaries in the coal mines, right, looking at that first and the last value to see what things were. We can also just look at the loss of our entire data set, right? So a loss of all of our X's against all of our Y's. Well, I want to do that point-wise, right? Where I'll point-wise compare the MSE of a given data point against its label, and that'll give me the loss for everybody. Well, and then I can do the sum of this. So this is our total loss of our entire data set. And that's what we want to optimize, right? When we do the stochastic gradient descent, we're just looking at the loss of a single data point, right? Remember that the loss that we compute in our training loop is just the loss of a single data point, not the loss of the entire data set. And that distinction is important, right? It means that we're not getting the global optimization, like the global best answer here. We're not computing the model of our entire thing because we're only passing in, remember, our first data point that we pass in, our data of 1, it's just passing in the single label and the single vector. So that means that we just get a single element at a time, and we compute the loss a single element at a time, and we get the gradient a single element at a time, and we get the update a single element at a time. And that means that the direction of the gradient that we go might not be a global optimum, right? Because it might be the correct direction to go for this particular data point, but that data point might be an outlier. It might be a red herring. It might throw you off the trail. And that means that our walk down the gradient descent function, right? Our walk down the slope of the loss function that you can kind of imagine as a hill, and you're walking down the hill, and you would think that it would be advantageous to walk as straight downhill as possible, right? And if we did the loss of our entire data set all at once, we would get the perfect answer. We would get the exact way to optimize our data all at once and which direction is the best way. If we do it a single data point at a time, well, we're gonna meander a little bit as we walk down our hill, right? You can kind of imagine it like a drunken stupor, stumbling your way down a hill. You're taking lots of individual data points. Not all of them are going to steer you in the right direction, but hopefully enough of them individually will that you work your way down. Now there's an advantage to this drunken stupor, and that is it kind of helps explore the space a little bit more. Because in general, we're talking about very, very high dimensional spaces here. We're not just talking about 2 dimensions. We're talking about many, hundreds, potentially thousands of of parameters that we're tuning, right? In this particular model, how many parameters are there, right? Well, there's the model.w, which has 6 values in it, right? 3 times 2 is 6, plus the number of parameters in the model.b. Oops, I want to do the length of model.b. So this is a 9-dimensional space that we're moving about in, right? Because there are 9 different directions that we can move our gradients and things. Our minds aren't good at thinking about this, but it's the same concept as walking down a 3-dimensional space. It's just, there's many more ways to go. And so this is, in some ways, a blessing of dimensionality, right? If you only have one dimension, it's very easy for you to imagine getting stuck in a local minimum, right? You're going downhill, and if your slope function, actually, let me just animate this. This is an easy thing to scribble on my screen with, so here you have your x-axis, your y-axis, and say your function that you're optimizing looks something like this, right? Where you have a bunch of local minimum. Well, if you're doing a gradient descent and walking down that hill, you'll walk down here, right? And you'll walk, and then you get up here a little bit and you fall back down, right? The gradient descent just kind of sticks here. But if there are many dimensions amongst which you can move, well, there's probably some other dimension you can move that is, will keep you coming downhill, and then you can work your way downhill farther. And so it's kind of like, yeah, I think of it as the opposite of the curse of dimensionality. And in machine learning, you kind of exploit the fact that there are so many dimensions that local minima aren't very common. And in fact, if there are local minima, then the drunken stupor meander down this hill is kind of beneficial, right? Because you can kind of jump around a little bit and meander your way downhill. So that's the way that we're going to work on this. Just to refresh our memories here. So the sum of our loss is 600 sum. And let's train our model, right? So it's as simple as going through here. And now we just run this a bunch of times, right? We can just copy and paste this, run it, and see what our sum of our loss function is. And sure enough, it's getting better. Awesome. So hopefully we're learning, right? The loss function is improving. So how can we go about improving this even farther? Well, one way would be to grab, to just iteratively do this a lot of times, right? So you could write a for loop for step in 1 through, say, 100 steps. Actually, let's time it first. That's a decent idea. Before you do any sort of big for loop, get an understanding of how long it's going to take, right? So this takes about 0.7 of a second. Cool. So I can do this for about 100 seconds or 100 times, and it'll only take about 7 seconds. So let's do for step in 1 to 100, and just train this guy. That'll take about 7 seconds to do and give me a bunch of walks through my data, right? And so that will give me, more reinforcement of my training set. I could potentially add more training data too if I wanted to, try to make this a little bit more robust. But for now, we can just stick with this, and let's see what our sum of our loss function is again. Aha, it's getting better. Let's look at some of these canaries in the coal mine, model of x's of 1, and see how we're doing. So remember, this is our apple, which means it should be a 1 hot in the first position. And sure enough, we're getting a high value here and low values here, which is pretty awesome, right? That's exactly what we want. So this is, the beauty of Flux is that, the same 5 lines of code here that I started with, that I built, that it's totally extensible. And the only thing I changed was, how I defined my data and how I defined my model. Everything else was exactly the same. All right. So that is how this works. We can then go ahead and do the same sorts of visualizations that we did before, right? And let's see, I think these are in our, yeah, here we go. So in this example, we have some visualizations ready to go at the bottom where you can just plot a bunch of these things. So I just scrolled down to the bottom and plotted these, and let's open up my plots pane. So here is my plot. And with the way that these plotting functions work this time is because we now have 3 outputs, we essentially have 3 decision variables, right? There are 3 questions our model is asking. The first question is it a, let's say, is it a banana, right? And if we're on this side of this line here, this line is where our model gives a value of 0.5 in the position of the banana, which is the second one, right? So given an arbitrary data point here, this will say that the value of that is it a banana question is going to be 0.5. If it's on this side, it's higher than 0.5. And if it's on this side, it's less than 0.5. So this area here is our banana area. I can draw a crummy looking banana here to kind of represent, over here, we have bananas. We then have a second decision variable of our apples, right? That is asking, is it an apple or is it not? And again, same idea, right? If we're on this side of this line, we have apples. If we're on this side, it's not an apple. And same idea, this line is representing where that model evaluates to 0.5 in the apple position. I guess if I were to draw this, it's 0.5 like this in the first position of our one hot, and then something and something else, right? It doesn't matter what those 2 values are. This is only looking at the apple. And then the third decision variable is the grapes. And again, same idea. You can look here, this side of this line, it is a grape. On this side, it's not, and so on and so forth. But there's a problem here, right? In that all of these lines are straight. They're all straight lines and if I wanted to create a real line that distinguished my apples from my bananas, well, I'd want it to curve, and I'd want it to be red. I'd want it to curve around, right, and reach in here and grab these guys and come back out. So that way, this is my apples section, and outside it's not. Instead, I have this section here that these are all bananas, at which my model is saying, well, maybe they're apples. And so this is, where we need more dimensionality in our model to represent the more complicated shape here, right? And if you look, there's going to be some section of our model where we're not going to be able to do much about, right? There's this overlap here between my reds and yellows right here, where I have reds and yellows overlapping. There's no way my model will be able to tell those apart because I'm only giving in these 2 features, right? I'm only giving in the average red amount and the average blue amount. And so my model's not going to be able to distinguish in this zone here, right? It's going to be stuck when it's in that area. And that's okay. That's a limitation of my feature set that I chose. I could choose to add more features to make that, to help distinguish that point, or choose different features. The beauty of using only 2 features here is that we can visualize it like this. And so that's why we're limiting ourselves to that. But of course, there are many other features we could use in our data set. So let's extend this model and make it a deep neural network and try to add more complexity to our model itself to hopefully be able to curve some of these lines a little bit more, right? Curve some of these decision variables, add dimensionality in the structure of the data that we're able to represent, right? So our data is higher dimensional than what we're using to detangle it. And so then we're falling apart. So Notebook the next notebook here is going to kind of walk through that. Let me clear my scribbles here and stop annotating. So that is, the basics of multiple outputs. What we want to do now is add a layer to our network and go to a deep neural network. And that's what Notebook 17 talks about. And it does so by walking through a bunch of pictures. And so I'll pull up those pictures on my in my notebook, in my browser here, and I can walk through them as we talk about them. So say I have, oh, right, I need to go back to here. So say I have some data set I'm trying to fit, like this data here. Let me make this a little bit less busy on my screen. Okay. Say I have this data set here that I'm trying to fit with some machine learning model, right? I want to fit this, and if I were to just do a linear fit, right? Just do that W's times my inputs. So I have, my X's, my one feature down here, another feature up here, and I'm trying to encapsulate this behavior, right? I'm trying to represent this behavior, describe this behavior with a machine learning model. Well, if I simply have a, a linear model, that is some linear algebra transformation like a multiplication and addition, like, for example, taking my W, multiplying it by my input, and adding some bias. Well, that's essentially the same as drawing, what? Why did that? There we go. So that's essentially the same as drawing a line through my data set here, right? I can draw a line through my data set. I can fit that data. Of course, it's not going to fit very well where there are nonlinearities, right? I can encapsulate most of the linear behavior here, but it's not going to do very well when I have nonlinearities. Well, I can do a little bit better by, adding some complexity to it, right? So if I were to, add some nonlinearity to this data, well, how would that look like, or how does that behave? Well, one way that you can imagine this is by, using that linear transformation to do a rotation sort of operation. So matrix operations can be viewed as or imagined as rotations of the Cartesian plane and transformations along those lines. So I can rotate and transform my Cartesian plane and work my way down here by simply taking this, oh man, where did that go? There we go. So doing some linear stretch, transform here. So this is the same data set here, just transformed by rotating it. And now I've removed that one major linear offset, and now the nonlinearities shine through, right? And now if I were to simultaneously append some sort of nonlinearity, right? So some sort of, system, some line that is nonlinear, so say like a ramp function like this, that encapsulates a little bit more of the nonlinear aspects here. You can do that, you can fit that simultaneously, account for that transform, and then you can subtract that out and move to the next stage. Well, the next stage, you can, so this is exactly that. It's just that graph that I showed before, but with that first nonlinear section accounted for. Now, what gets output here? Well, it's just more data that gets output. And that data could be fed into yet another layer of a neural network. right? And so if we stack the outputs of a neural network as inputs to another layer of neural networks and so on and so forth, right? Remember, each neural network can have multiple outputs. And so those outputs can go into new inputs. Well, now I can have another linear transform, right? And remember, the first step of our neural network is to do some sort of linear fit, right? I don't know what the best linear fit is here, but it's something like this perhaps, where you try to encapsulate the behavior. And again, then you do that transform. You rotate, you shift, you change where that transform is, and you adapt to it, and you subtract that out. And then you get the next step in your thing. And as you go, you're accounting for more and more of the behavior. So this is a cartoon image of what a deep neural network might look like, right? And so what you have is, you have these single layers of neurons. So this is a representation of a single neuron layer with 2 inputs and 3 outputs, right? And we know what happens here, right? What does this look like? Well, what's happening here is we have 2 data points for each element in our data set. And we take those 2 data points and we multiply them by some outputs, right? And add them together and give ourselves some W and some B's, right? And so this image here is representative of a matrix vector multiplication, right? Where we have a vector coming in, we have a matrix of W's here, where what is the shape of this matrix going to be? If there's 2 inputs, 3 outputs, well, it's going to be a 3x2 matrix. And then we'll have 3 outputs and 3 biases here. So you have a 3x2 W and 3 B's. And then we apply some nonlinearity and it comes out the other side. Well, then we could have a multi-layer neural network, right? Where we have many of these guys, right? And you can imagine how this looks, right? Where you have many of these images where you can go in and just stack them on top of each other. So what's happening here? Well, we have our first network, right? Let's call it this purple network that is our, 3 inputs and 4 outputs. So that's a 4x3 W plus 4 B's, right? So this is a W, there's a B here that has 4 elements, and then some nonlinearity. And those 4 outputs, they just get jammed straight into another network here, right? That is kind of a hidden network. That is a hidden layer is what it's often called, that is purely internal, right? There's no the outputs here, you don't ever observe, you don't see them directly, they just get sent directly into another neural network. And so here, this one here is 4 inputs, 3 outputs. So that's going to be a 3x4 W and 3 B's here and so on and so forth. And then the outputs of this one, let's use red. So this output here, this is our final output layer here with 3 inputs and 6 outputs. So that's a 6x3 W plus 6 B's and plus some nonlinearity. And we end up with 6 outputs here at the final stage. So by adding all of these weights, we're adding lots of complexity. And the important part here is that after each stage, we have some nonlinearity. And what that nonlinearity does is it prevents this composition of many linear transforms from collapsing on itself, because multiple linear transforms together gives you a linear transform. But these nonlinearities, those kinds of bumps, you can think of it in the data, those preserve the structure here, and they're kind of what allows you to do this and allows you to have many layers and stack these things arbitrarily deep, arbitrarily wide, that allow you to add. So we're adding lots of parameters that we're going to take the gradient with respect to, right? So in this single image, how many parameters are there? Well, there's 12 here plus 4 is 16 plus another 12 plus 3 is 15. So that's 31 plus another 3 times 6 is 18 plus 6 is 24. So 31 plus 24 is 55 parameters, if I did my math correctly here, right? 55 parameters that are all going to take the gradient with respect to each one separately and tune them simultaneously. So the cartoon structure that I walked through earlier, just kind of going through that bump and shift kind of thing, that's not totally accurate. It's just a little bit of a cartoon representation to hopefully help you understand a little bit better how these things work, right? How we kind of can think of them as working. And the goal there is just to kind of give you some understanding of the linear versus nonlinear aspects here. Because if I were just to do a bunch of linear transforms, well, it's just shifting around my paper, essentially, shifting around those transforms. And you could just go straight to the end result. So it's that bump in the middle that we're simultaneously fitting against, essentially, with our gradient descent algorithm to do. So let's extend our model from the last time to do this. And I can clear my drawings again and stop annotating and go back to my editor and jump into notebook 18 here, where we can build a neural network that's going to have 2 by 4 by 3 that will give us a 2 by 4 by 3 network. So how is that going to look? What's it going to look like? Well, this is a little risky. I don't know that I have all the tools installed to draw this right now. Oh, yeah, I think I'll skip drawing it for right now. Let's see, do I have this saved? I don't think I do. I should have that saved. Yeah, that's all right. The goal here, right, will be 2 inputs to an output of 4, right? So we know how to draw that dense neural network, right? That's going to just be, yeah, well, why don't I just scribble it on my screen instead of asking Julia to draw it for me? That'll be easy enough. So 2 inputs, right, to 4 intermediate variables. So 1, 2, 3, 4, to 3 outputs, 2, 3. And all of these guys are connected together, in a dense fashion, right? Like what we had seen before. That's why these are called dense neural networks, because all of the connections are connected to all of the preceding values, right? So you go from, it's like an all to all sort of network here. So 2 inputs, 1, 2, 3 outputs. And if you wanted to, you could include this draw neural network file to give you a pretty representation of what I just scribbled here. But how do we define that in code is the better question, right? Drawing it is one question. Defining it in code is another one. And the answer is relatively simple, right? We know how to build a model that is a dense network from 2 inputs to 4 outputs. We know how to build another model that is a dense network from 4 outputs to 3 inputs. So this is like layer 1, right? That's a layer 1 of our model. This is layer 2 of our model. We just need some way of chaining them together, right? Where if I define these guys, so we have layer 1, layer 2, and if I call layer 1 on my first element of my x's, I'll get 4 outputs, right? Let me hide this. Let me get this a little bit there. Okay. So layer 1 on my x's gives me 4 outputs. Oh, well, yeah, I should add a nonlinearity here, right? Because otherwise my networks won't collapse. By default, there's no nonlinearity if you don't have it. So you can optionally add a function here called the activation function to give us that nonlinearity. That's an important step if we're going to stack together 2 layers. So let's do that. So layer 1 gives me 4 outputs, right? And then layer 2, what's that going to give me? Well, that I want to take those 4 outputs and pass them to 3 outputs, right? So these 4 outputs, they're kind of meaningless, right? I don't have 4 of anything here, right? I have 3 grapes or 3 classes of things, right? I have apples, bananas, grapes, and I just want to set this up to work with them that way. So how do I do that? Well, I just simply take this middle output, let's call it, or maybe actually let's call it hidden output, because it's something that you typically don't see, right? You don't see this 4-element hidden output. It's just a in-between step that we then call layer 2 on our hidden output. And this now gives us our 3 outputs here. And that gives us the final answer that we're looking for. And of course, again, you might want that sigmoid transformation to cap these things between 0 and 1. So you can think of it as 0 and 1. We'll talk about a little bit of a better way of doing that. But let's transition this to our real world data now, right? So we had our example. Let's go back up here. Let's find our entire solution, right? This was our entire solution of all of these things. And let's just copy this and paste it. We'll use the same data. This actually uses the same data as before, does through all the same data munging to get this all set up. You can run this again. It doesn't matter. We're in the same Julia session, so you don't necessarily need to run this again. We're not going to change anything about our data this time. What we're going to change is our model. So let's implement that, right? So I'm just going to jump ahead, not bother running those data sections again, because we already have our X's and our Y's. In fact, we already have our data already defined for us. Well, what I want to do is I want to define my model here. So how do I do this? Well, let's set up my model in a way that I can chain these things together, right? I could define this as a composition of these 2 dense neural networks, and the way to do that in Flux is we do what's called a chain. So there's a chain function built into Flux here that just chains multiple layers functions together. They're just called in sequence. And so you just pass in all the layers into your chain, and they'll just work their way through your function in a way that you can get them going. So let's do that. Let's chain together a dense neural network from 2 to 4 with a sigma, and then a dense neural network from 4 to 3 with a sigma. Right? That's kind of the way that we've been doing this before. I'm going to change one thing about this, and that is, we're constraining our outputs here with this final nonlinearity to be between 0 and 1, right? We're saying that these things must be between 0 and 1. And really, we want to think of them as probabilities, right? Probability that it's an apple, probability that it's a banana, something along those lines. So there's a really nice, statistical way of thinking about this. And if I don't constrain this output, so I allow the final dense layer to be a purely linear layer from 4 inputs to 3 outputs with no nonlinearity at the end, that means that my function can range, from -infinity to +infinity. The outputs are unbounded, essentially. And I allow my model to kind of explore the space a little bit more. There's a really nice statistical way of interpreting those values, which is called the softmax. And this is something you might have heard before, so I'll just look up the help on it. And the softmax here, what this does is it turns an array into a probability distribution that sums to 1. It's doing some fancy statistical thing that if you're interested in statistics, you can dig into. In fact, there's a link here to the Wikipedia page if you want to understand a little bit more about it, how it works and the theory behind it. but it essentially, scales our data such that our probabilities add to 1, and it assumes that the inputs are unbounded and can be negative, can be positive, can be arbitrarily large or arbitrarily small. And so this is a nice final layer to my chain of functions, right? Remember that we just take the input from one function, pass it along, and pass it to the softmax function as a final output step. And what that means is that then I can interpret my entire model as probabilities, which is awesome. That's really what I want out of this. I want the probability that it's an apple versus a grape versus a banana. The loss we can define the same way. We can go through this and train. Now, the tricky part is this is now training significantly more parameters, right? 2 times 4 is 8, plus 4 is 12. So 8 parameters in our W plus 4 parameters in our B for our first layer, right? And then for our second layer, we have 4 times 3 is another 12, plus 3 is 15. So we have a total of, what is that, 27 parameters that we're tuning here. And that's starting to get a little big to train all of these things. And then how many parameters does the softmax function have? Well, 0. There's no parameters that are tuned there. So Flux just ignores it and passes it along happily as part of its chain. So, just as before, right, my model, what is the type of it? The type of it is a chain. And just as before, I can ask for what are the params of my model. And now I'll have all 4 of those arrays, the 2 arrays from my first layer, the 2 arrays from my second layer, all put together here, which means that I'll get the derivative with respect to all of them as well. So now we need to train this. You can, again, look at the sum of our loss functions, right? And you want to, keep training this until you improve on that sum, right? And it kind of is slow going here. And in fact, if I ask, how long is this going to take me here? It's about the same as it tends to be about, 1/10 of a second or so. So it's a little slower. And it's going to be a little bit slower to converge as well. So if I do that same for loop that I had done before, this will take about 7 to 10 seconds based on the single times that I had done here. And then we can look at, what is our sum of our total losses? Hey, we're doing pretty good. All right. So let's see, did I actually evaluate that model? Yeah, I did. Okay, good. So now we can go back to the exact same, the same plotting routines as we had before. Go in here, just put them right here, do the exact same thing, plot these guys out. I'm just grabbing the same plotting routines from before. Again, this notebook will walk this through with you a little bit slower and more incrementally, but hopefully let's see if this worked. Then we can pull up our plots pane here and see here, sure enough, our 3 models now are doing extraordinarily well, right? They've gained some understanding here. And in fact, the red value, the red contour is right up against our green contour. You can barely see it there, and right up against the yellow contour. Maybe I should change the order in which I plot them. So that way the red plots last, because that's the one that's the most interesting here. Let's rerun all of these guys. Oh, that's not significantly better. Shucks. I had hoped that plotting the red one last would, oh wait, I was plotting, yeah, I want to do this one last. The contour is the important one to do last. Okay. There we go. Now my red one's plotted last. That's what I really wanted to see here. So all 3 of my contours have kind of smushed together. And now we have 3 very clearly delineated regions, right? Where, let's pull up my annotations just one more time here. We're just about done with this lecture, and that puts us in good shape for our last hour. But let me draw a little bit to describe what's going on here, right? So we have 3 now very distinct regions, right? Where this region up here is, this side of the green arrow. It's also outside of our red region, and it's also outside of our yellow region. All three of our regions here are completely independent of each other, right? Where we have an area where the red output, or the apple output of our model, when that is above 0.5, all of the others are less than 0.5. Well, that makes sense. It kind of has to be that way because we're using that softmax normalization. So if there's any point at which our model is above 0.5, that means that the other two values must be less than 0.5 because these outputs must sum to 1. That's the kind of definition of our softmax function. So that kind of gives us these three distinct regions, which allows us to really concretely understand them as, this is our apple region and our banana region and our grapes region here. We have our three very distinct regions, and we gained this nonlinearity. How did we gain that nonlinear, reaching in? Kind of like I drew, remember, I almost drew exactly this curve in the previous lecture. And it's what I wanted to have happen because I needed to separate out the apples from our grapes above and the bananas below. And our model now has learned that from absolutely zero, I didn't give it any intuition here. I didn't give it any knowledge. I simply started at a random starting point and said, hey, train, let's see what we got. Let's train this and make this happen. So this is the power that we get. And again, constraining ourselves to two features allows us to plot these things and plot the model outputs in a nice concrete way. But then I can also just kind of see what happens at arbitrary points, right? So I can clear this. And you can imagine evaluating my model here. So let's say this point right here, 0.25, 0.25 looks kind of interesting, right? It's right at the confluence of those three contours. What's happening right there? Well, I can simulate that data point, right? 0.25, 0.25, and just ask my model to evaluate it. And sure enough, it's, not very sure about which one things are here. It is, somewhere right here, and boy, it looks like that's a pretty steep line because we're 0.6 grape, which is the green, 0.3 apple, which is the red, and 0.05 banana. And because we use that softmax normalization, you can kind of think of these as percentages, right? 30% like a grape, 5% like an apple, 60% like a banana. So it's not 100% certain about any of those. If I nudge this, let's say nudge the Y down a little bit, then I get even more uncertain, maybe 50% apple and a quarter chance of either of the other two. And that's like right at this confluence point. Or I could move over, say, let's go to 0.5, 0.22 maybe. And this is, we're very confident actually, 0.5, 0.22, or somewhere right in here. We're right in the middle of this blob of bananas. And so sure enough, we are 93% confident that it's a banana. We're very confident that it's not a grape, right? Grapes are all the way up here. And we're 6% sure it's not an apple. So that's kind of how you can play with this and see what these things look like. If I shift up on the y-axis, well, I lose some confidence in my banana, gain some chance that it might be an apple, and so on and so forth. So it's a lot of fun to play with this. Encourage you to poke around at this. Again, this whole notebook here, there's more depth to it that you can work your way through. But it's essentially what we walked through, right? You can see how you train it, play around with it. There's a little bit more about batching. And we'll talk about how that works in our next notebook instead of digging into it here. But this will walk you through that a little bit more incrementally. So if you have any questions about batching when we get to it in the next hour, you can come back here and play with it a little bit. in this example. And sometimes stepping back to simpler examples allows you to understand more complicated features. But I really want to get to a more comprehensive example, move away from our fruits, the standby fruits, and talk about something that's a little bit more hands-on and more exciting. So with that, any questions here about what I did? Really, just to kind of recap, the only change that I made, again, is in my model definition. And this time I didn't even change any of my data. I just changed my model to be a chain of 3 things together. Yeah.
So, hey Matt, this is Amit again. So, very high level. So we started with 2 features. Okay.
Mm-hmm.
Now we have decided, okay, we are going to use 2 layers,
Mm-hmm.
and so layers can. I'm thinking when we are visualizing in terms of dimensions. So what do we achieve if we add some more layers? Will this perform any better? How do we decide how many layers are good enough, and how many features are good enough? So how do we decide in those?
That's a great question. And it's a question actually that stymied machine learning for about 30 years. The basics of neural networks have been around since the 60s. And folks really loved that single layer of what the single layer does. The single network, the multiple input, multiple output scheme works really nicely. But there is a trap for mathematicians in that there's a closed form solution here, right? If you're just doing a linear regression, which is all a single neuron layer is, it's really just a linear regression with some nonlinearity applied to the output. If you're just doing a linear regression, there's a closed form solution. It's called the normal equation. It allows you to very succinctly and comprehensively get to the perfect answer in one step just by doing some really clever matrix linear algebra. What folks realized is that as compute got cheaper, even though there's no closed form solution, there's no perfect answer here, there's no mathematical answer that says, hey, for this problem, a wide network is going to work very well. Or for this problem, a narrow but deep network is going to work very well. There's no real, mathematical or statistical grounding there. What happened instead is that compute got cheap enough that folks could just try it. And that's really where machine learning has gained its legs in the last 20 years, is that compute became so cheap that you can just try a bunch of different configurations, test it, and see what works best. And that is kind of the art form of machine learning. It's kind of a mix of a science and an art, where you kind of play with the structure, you get some intuition of what might work well, and there's some things that can help you there. So for example, in grad school, one of my colleagues did a very rigorous understanding of high dimensional spaces in neuron firing rates. So he was doing, looking at the neurons of the brain and how they were controlling your arm moving around, and tried to figure out, what's the latent dimensionality, the latent space that the neurons from which he's sampling is representing. And in a very clever kind of way, he tried a bunch of deep neural networks and found that the ones that performed best were the ones that matched the latent dimensionality that his hypothesis, his thesis said there probably were about 11 latent dimensions here. And so he took the number of inputs, had a hidden layer with 11 elements, and the number of outputs again. And so that was kind of a cool thing. And that's kind of the structure that academicians really like to take. Like if you're in academia, they really like this kind of very rigorous way of thinking about, puzzling about it, trying to get some real world intuition because you're trying to figure something out. But in industry and in the real world, often you don't care what the thing is, you just want your machine learning model to do well. And that is the essence of machine learning, and the essence of what modern machine learning is doing is that you just try a bunch of things, see what works. Now, you have to be careful that you don't overfit your model selection as well as overfitting your training data. So just as you want to hold out some data to test your model against that you didn't train on, to kind of get an understanding of what's the naive performance of my model had it not seen this data point before. Well, you also want to kind of hold out some data after you've tested a bunch of machine learning model pipelines or model definitions. So in this example, you might want to try another model that say only has, let's say just has 2 intermediate outputs here, right? And see if this can do as well as the other one did. And you know what? It's easy to test, right? You just change that one answer, and now we train it a bunch of times again. And we just go through, train this, go through a bunch of steps, train it a whole bunch of times, and see if we can do any better than what we did before. Maybe we'll gain some efficiencies because now we have fewer weights that we need to train. So maybe we'll train a little bit faster. But in the trade-off, maybe we won't do quite as well at our plotting. And so we can go in and see, are we doing as well as what we were before? And sure enough, this still represents our data pretty well, and was able to train it in just 100 loops through our data set, gives us something that looks reasonable. It looks different, right? It's a different structure, but again, it's also reasonable. And the way to test these two things to see which one is better is you'd want to have some holdout data that you could test and see, well, which one's doing better. And then you can use that model in your production. So that's why it's so important to have just a very simple algorithm at which you can play with, right? That you can change what these things are, how they work. You generally want to use the smallest network that can feasibly represent your data. Because the bigger the network is, the longer it's going to take to train. And training time, that's real world money. And so hopefully that gets at the question. It's one of my favorite questions to get during this course because there's no right answer.
So it all depends on like what do you want to get out of it. Suppose I'm happy with the 90% accuracy,
Yeah.
You know what, I'm going to stop. That's it.
Yeah, exactly.
Yeah.
Yep.
So when you train, so computation, does it depends on, well, I'm just still the same question, but in a number of features or number of layers? So for example, the reason I'm asking, we have got huge data set, and I was trying to train on this huge data set. So there was a trade-off. We said, okay, you know what, we are going to use less layer, but more features, but less features or more layers. So there was a trade-off, and we couldn't figure it out. Like we had data like about 5 gigabytes of data, simple market, buy, sales, purchase, order country. It took 36 hours. So that's why I was confused. Like, what should I use? Like, how could I make it faster?
Yeah, that is a very tough problem. In general, you'll see, if you as a data scientist can put together a reasonable hypothesis about which features are going to be most important, and you can select those without much consternation, it is much better for you to figure that out than it is for the machine to figure it out, right? It takes far more compute for the machine to do the kinds of things you already know. And so if you're able to do those things, then great. And I would say do them. In fact, a lot of my time when I was working as a machine learning engineer at the University of Chicago's Data Science and Social Public Policy program was the feature engineering, where we were trying to express, time series in features that the computer could crunch on efficiently and make sense of. So for example, converting time series to a feature, you might be looking at, number of events within the past month or number of events within the past year instead of the raw time series, because the raw time series is harder to work through essentially and requires far more algorithmic computation than the simple, feature engineering that I could do as a data science engineer. And so it's a trade-off, again, between cost, right? How much are you willing to pay your engineers to do the engineering of features versus compute to try to figure those things out yourself?
Yeah. Thank you, Matt. You answered actually. Funny.
There's no easy answers here.
Yeah, no, exactly. We hired, actually, no offense, but we had H2O.ai people in our campus, and we paid them that's what they answered me. They took simple data and they took like 40 hours of training, and they came back and they asked me, okay, you want less features or you want less layers? I said, how the heck I know? You tell me. So
yeah.
that was H2O people. So I'm going to try this, like doing this in Julia. Maybe,
Yeah.
they claim H2O driverless. It tells me how many features versus, the layers I should be using, which they couldn't. So I'm going to try this in Julia now. Thank you. I think that answers my question.
So yeah, let's take our last break. If y'all don't mind, let's make this one a little bit shorter so that way we still have about 45 minutes for our last hour. And in our last hour, we'll talk about really this notebook 19 is kind of the final notebook in the course. The last 3 here are kind of fun little demos that we can talk about at the end if interest and time allows. But 19 is kind of the final comprehensive example. That's a lot of fun and a little bit more concrete. And I have some fun additions to this that we can look at then as well for how this will work in production and getting things going. So let's take 5 minutes if that's okay with folks. And we'll be back at about 1/4 and be ready to look at handwriting and a more fun task. So see you then. All right, welcome back. So Peter, just to get to the question that you had asked a few hours ago about speed comparisons and if there were updated benchmarks, I had asked on our internal machine learning channel. It does sound like a lot of them are still outdated, and we need to rerun them and update those things. So we don't have up-to-date benchmarks. It's something that we need to work on, particularly because it also helps us target where optimizations are needed and such. But yeah, hopefully we can get something like that up and running soon. All right, so for the last notebook here, we are going to do a pretty cool task on handwriting recognition. And there's kind of this hidden web page on Flux. So this is the Flux website, like the main entry point for learning about Flux and Julia, getting things structured and set up this way. So this is how you can look at documentation. There's a blog here. There's also a secret page, and it's secret because it's not very well supported. It's not, it's not being maintained very well, but I like it because it's kind of fun. It's this experiments page. And the game that we're going to play today for our last hour is this MNIST classification. The MNIST dataset is kind of like the hello world of the machine learning world. It's the example that everybody uses to play with and see, what's going on. So this is the final trained output of a Flux trained model that that does machine learning recognition of handwritten digits. You can play with it, see whether it thinks something's a 1 or a 2 or what it is. It's not very well trained right now, so you'll find some weird cases where you can kind of trick it. It's fun to play with, right? You can kind of see, make these awful looking diagrams and try to see, what are these things? What does it think they are? It's kind of fun to play with. But the goal for today's last lecture is to put this together, right? And we now have all the building blocks to do this. We know exactly what needs to happen, right? The only missing part is the data itself, right? We need training data. But once we have training data, well, what are the inputs and outputs going to be? Well, inputs could be, some features of our image itself. We know lots about doing feature extraction. And outputs is just going to be a 10 element one hot vector that just says whether it's a 0, a 1, or a 2, or a 3. And you can kind of see, the bars on this demonstrating the model's output for different things. And of course, playing with it can, make things more or less certain of what your terrible handwritten digit is. But let's look and see what this looks like in Julia. How would you build this model in Julia? So that's going to be our last lecture here. So the notebook 19 is what we're going to go through. There's some more data about the MNIST data set. Wikipedia has an article about it, and it talks about where this data came from. I think it comes from Census. Yeah, Census Bureau. So the Census Bureau put together all of these things, and the testing data set was actually from high school students. So these are two separate data sets, right? Completely distinct, but both representing numbers. And so hopefully training on one will generalize well to our testing data set. That's the way it works. It's a nice way of getting things going and testing them. So how would we do this? How would we set up a notebook? Well, first we need to download the data. And the Flux package itself, since this is such a canonical data set, it packages it for us, which is awesome, right? So you have flux.data.mnist is a package or a submodule of Flux that gives you the labels and the images. So you have your labels here and your images, and they're all set to go, ready for you to play with, right? So we have labels are, all of these labels. Let's just do labels of 1 through 5, say. Look at the first 5 labels. So hopefully the first 5 images will be 50419. I'm going to pull in the images package just to allow me to visualize the images themselves. Images, as you all know, are simply they're simply arrays, and so you don't necessarily need the images packages loaded. But if you have it loaded, then looking at the first image will pop up that image in shucks, if I have ImageMagick installed. You need to add the output engine so that way Julia is able to write things to a ping, so that way it can put it in your plots pane. Let's see if that works. So the key magic here is add images and add ImageMagick, which gives you output to libping, and then the image itself will appear in your plots pane. And I could move this. Why don't I move this plots pane over here? Because then I can play with it a little bit more directly. So images 1 is a 5, images 2, 0, 3 is a 4, 1, 9, right? And those match the labels 1 through 5, right? Is 50419. Cool. So that's our data, right? We have our labels and our images. Well, we need to figure out how we're going to make these things into features, right? Where we want to make them into the features that we need. So how do we do that? Well, let's, what could our features be of our images of 1, right? Well, it is itself an array of gray values. And just like before, right, we could convert this into a floating point, float of our images. And that will, oh, why didn't that print out? I guess I need to do float 32. There we go. So that'll give me my raw values there. So asking for the float 32s, I don't need a high precision here. These aren't high precision values. They're grayscale values. And so the float 32 will encompass their behavior quite nicely and give me a little bit more performance out of it. So I have 28 by 28 pixels that represents this image. Zeros around the outside are black, and ones representing the inside, which is the white section. So the only thing that prints out here are a bunch of zeros, not very interesting. So I could try to do some like mean value or some feature extraction like we did with the apples and bananas. But really what I want to do here is just, use the vector of all 784 elements as my input. So I can create a function here that just says pre-process and takes in an image and gives me back the vec of the float 32 of the image. And that is, my feature engineering, right? That's the feature creator function that kind of takes an image and creates a feature from it. Similarly, I need to, create my labels out of them. And how do I do that? Well, you remember you have the flux.oneHot, right? That gives me, say, so for this one, I want to say that the 5th value is hot out of 0 through 9 are my possible elements, right? The labels here are off by 1. They're actually, you could consider them 0 indexed in some ways, right? Because the first element is going to represent the digit 0, the second the digit 1, and so on and so forth. So my flux.oneHot function, right? I can do this, and that'll give me my 10 element vector, those are all my outputs, right? And the sixth one, or my fifth, representing the number 5, is going to be 1, all the others 0. If I want to do this, across my entire data set, right? Remember that, the first bunch here is like 5, 0, 4, 1, 9, or the first 5 labels. And I wanted to do all of them at once. Well, I can't do it this way, right? I want to do it pointwise across these things. And if I tried to do a pointwise operation like this, it's going to try to match these things together. Well, I want 0 through 9 to always be a value, so I can just put it in an array, and then it'll pointwise broadcast the array itself over each element and give me 5, 0, 4, 1, 9. So those are my labels, right? And I can do this for my entire label data set and create an entire array of labels. So then I can, let's take, for example, the first, 5,000 images. So we can say, all right, let's, look at my X's is going to be pre-process all of my images of 1 through 5,000. Just take that as my test data set. Remember, we have lots of images here, right? Length of images is 60,000 images that we can train on. I'm just going to look at the first 5,000 to make things a little bit easy on my computer, to make it a little bit more computationally tractable. So I can do that, right? I can pre-process all of my images. Oops, but I want to do it pointwise across all of them, right? I want to apply this pre-process function to each image. So I do it pointwise using broadcast notation like that. And that gives me an array of arrays of all my data points. So those are my X's. I can do the same thing with my Y's, right? And just do that flux.1hot of my labels of 1 through 5,000 and 0 through 9. Of course, again, I protect, you can kind of think of this, protect my range in a vector. So that way this vector applies to each one of my labels appropriately, or the range 0 through 9 applies that way. It's kind of a nice way of doing that. So now I have, oops, again, pointwise, keep forgetting those dots. So again, 5, 0, 4, 1, 9. It's kind of nice to do these little sanity checks, make sure that things add up and look okay. So there's my data, right? X's and Y's. Now let's go back to my, my Flux core algorithm, right? So here's my core algorithm, grab it. We'll bring it back over here. And now we can use this, right? Let's start off simple and start simply with a simple linear dense network. How many inputs are there going to be? Well, it's going to be the length of my first X's, right? Which is, what is it? 784, right? The total length of my first element of my data set. You can just grab that automatically. How many outputs am I going to have? Well, I'm going to have 10. And then we'll just start with a single layer here just to kind of start simple. And again, we can apply the softmax normalization. Since we only have a single layer, we don't need a nonlinearity. We can add a nonlinearity if we add more complexity here. So that should do us, right? We have a chain, we have a single layer neural network, 10 outputs, the appropriate number of inputs for our X's, we have our Y's, we can collect them in. We don't actually, in this case, our X's and our Y's are already shuffled, right? Unlike before, we've already, put together our data, we have it all together. So we don't need to, shuffle or collect these guys. We can just use the lazy zip data structure directly. We don't need to worry about copying it or shuffling things around because, we have them all set up nicely to run. So we can just zip them like this and move on with our algorithm without making copies or shuffling or doing things like that. All right, so let's define all these things and train it, right? And it's going to take some time. to do a single iteration over our entire data set is, now 0.3 seconds. That's a lot more time. Well, it makes sense, right? We have 700 inputs and 10 outputs. That's going to take some significant time to go through. So how can we test this, or how can we play with this? Well, let's see here. Let's look at our total loss, right? We can look at the sum of our loss of all our X's and our Y's and train again and look at the sum of our loss. And sure enough, that's going down. But really the loss isn't what we're after here, right? The loss is kind of the theoretical, how far are we from the best? Really what we want to know is, given calling model on our X's of 1 here. So remember our example is 50419. So 5, 0, 1, 2, 3, 4, 5. Hey, we're already got, after just a few iterations here, we've got this first element correct, right? It's saying 89% certain that it's number 5. And when you go to make a business decision, all you care about is which one's the most likely. So, pardon the siren if you can hear that. So we want to ask which one is the most likely out of these things. And to do that, really, we're not interested in the loss, but rather we're looking at the accuracy, right? We're just curious, what is the accuracy of my model's output? And how can I see which one's the most likely? Well, just like there's a one hot function, you can do the inverse operation of one hot by saying one cold. We want to take this vector and flatten it down to a single answer. So we can do flux.oneCold of our model given a set of options, 0 through 9. And that'll say, hey, 5 was the most likely one. So that's pretty cool, right? You can just kind of collapse this down to see, which is the most likely, and without looking at all of the probabilities. Flux.oneCold does the opposite of one hot. It's kind of a cute little pun that says, hey, we want the opposite of a one hot vector, do the opposite work of a one hot vector. So instead of going from a single value to a vector, take a vector and go to a single value. So our accuracy function then, given some output of our model, right? Or actually, let's do it the same way as our loss, right? Given a single X data point and a single Y data point, we just want to ask, hey, is flux.oneCold equal to our labels or our Y? So I want to change this so that way it's referencing the X and the Y that we pass in, right? So our accuracy function will just take in some data point, call the model on it, ask, hey, is that equal to our Y value? And we can just see, is that going to be true or not? So that is our accuracy function. And it'll just return a 1 or a 0, right? And that will give us the value that we want, is this true or not? And then we can ask for, what is the mean accuracy of our entire data set? So I'll put that next to my loss function here. And we can evaluate that, right? And we can just ask, what is the mean of the accuracy, or let's do it this way. Let's just ask, you can ask for the accuracy over all of my X's and all of my Y's. And that gives me, all of my answers here. Oh, oops, what did I do wrong? Oh, right, my Y's are also one hot vectors. So I also want to do one cold of them too. Just keep things the same as my loss. So that way I can, there we go. So now we can see that, and we can ask, using the statistics package, what is the mean of my accuracy of all of my X's and all of my Y's? And we're hitting about 93% accuracy here, which is pretty good, right? But again, these are my training data set, really, I want to know what's the accuracy of a test data set that I've never used before. And how do I do that? Well, I look at, let's pre-process some data that I've not used before, right? So images of 5,001 through 10,000, say, right? So the next 5,000 images, and do the same thing for my labels. Again, I need to just do flux.onHot of my labels of 5,001 to 10,000. Oops, I'm doing 1,000. I need 10,000. Right, and so then this is my test accuracy, if I did that correctly. Looks like I didn't do it right. Yep, I don't have my parentheses correct there. So pre-process happens pointwise across all of my images, and that's the parentheses that I was missing. And onHot needs my options between 0 through 9. And what did I do wrong here? Oh, right, I need to protect my labels. Oh, and onHot needs to happen pointwise. There we go. So now I have my test accuracy and my training accuracy. And this is really where the rubber meets the road. This is the number that you're really interested in, right? This number, hey, what is the test set accuracy? How good are we on a novel test set? So I could continue training this, right? And test out, if I run this some more, am I able to continue to improve this? And there's a bunch of ways in which you can iterate over this. What I've done before was saying did for loops. I can even do a lazy iterators.repeated data. Repeat my data set maybe 10 times or so, and that will iterators.repeat. I think. Oh, what am I doing wrong? I don't know. Towards the end of these lectures, I always go a little fuzzy in the brain. But I've been running this a bunch of times. There's a way to lazily repeat your data set, so Flux will iterate over it. But let's just look at my accuracy now. So I can look at my accuracy of my test data set, or whoops, I want the mean accuracy, right, of my training data set is that. So that's increasing 94%. My training accuracy of my test data set is this one, so 90%. So they're continuing to increase. There's some really cool visualizations you can do here to kind of watch these things go. But we're going to hit some wall here that we're not going to get significantly better, I think, than about 95% accuracy or so. And that's a factor of the fact, two reasons here why we're not doing that. One is that, well, it's just a simple one-layer neural network. So I could add another layer to this to improve my training. The other reason is that, I am only looking at a single pixel at a time. Both of these things can be rectified. Let's first, and the third reason is that we're only looking at 5,000 images. We could look at the entire 60,000 image data set to kind of help improve things. So let's iteratively improve the way that we do this. So the first thing is, well, maybe let's try making this a little bit deeper, right? Maybe you want to go to a common idiom within neural networks is, you have lots of features. Go down to some intermediate representation that is, maybe some, close to the output, but not quite as many as the output. So let's go to say 20 and then dense from 20 layers to 10 layers and still use that softmax. So then again, this would give me that extra definition. Of course, if I'm going to chain together 2 layers, I need a nonlinearity. And you might reach for that sigma nonlinearity that we've used in the past. That one's okay. but it kind of constrains what our second model can do, right? Because the second layer is only going to get numbers between 0 and 1, which constrains its ability to output the full range of options. It constrains its ability to output negative numbers. And so, there are some other fun examples. We can, for example, the question of what nonlinearity to use is an interesting one. Flux has a bunch built in, and we can just plot them. So one common one that you'll see that's kind of a fancy name that means something not fancy at all is called a ReLU, or rectified linear unit. And if we just plot this, you'll see what it is. It's very basic, very straightforward. It is just a ramp function. For all numbers less than 0, it's going to output 0. For all numbers greater than 0, it's just going to output the number itself. It's really basic. There's nothing fancy about it. And that can be a nice choice because it's so fast, right? It's just a single branch. If we're less than 0, output 0. If we're greater than 0, output 1. That can be a fun one to use. It's nice. The one downside is that think about how we get the gradients with respect to individual outputs. And our outputs are constrained by this activation function. And so if our activation function is down here in this 0 regime, the output for that neuron is going to have a flat gradient, and it's no longer going to change. This can cause what's called a dead neuron, where you get stuck in this flat region where the gradients can no longer affect it because it's being constrained by its nonlinearity to be 0, which is a flat gradient, which is a 0, which then kills off your neuron or kills off that weight and doesn't allow it to change anymore. There's some benefits to that, but there's also some significant downsides. And so, another such linearization function or nonlinearity that you can do. Again, it doesn't really matter what these nonlinearities are. They just need to be nonlinear to allow you to stack together these weights and allow you to play with them. You can do another popular one is tan H, which looks something like this. But again, that's constrained. It's a little bit better than the sigmoid because it's constrained between -1 and +1, right? So now at least we're outputting negative numbers from our layer. So that one can be helpful at times. And again, all of these things are things that you can play with, gain an understanding of. The last one that I want to demonstrate to you is flux.leaky ReLU, which looks a lot like the ReLU, but when it gets below 0, it has a slight gradient, right? It's kind of like a ReLU, but you don't completely kill off neurons. There's always a chance because the gradient here is going to be, just slightly enough to allow it to explore the space a little bit better, but it's still nonlinear, still allows you to change those. So let's use that one. That's kind of a good go-to, that leaky ReLU. That's a fun activation function to use. So we can, again, go through this and train this. So when I evaluate this function here, let me just hide my plots pane. Oh, why can't I hide it? Yes, I'll just close it. Okay, so when I evaluate this, it'll reset my model, right? It'll choose a new model. And when I choose a new model, it's going to give me a new starting point, right? A new random starting point for all my weights. And I can do that just fine. And again, then all of these parts just happily go along with it. But now I have even more weights that I need to train, and it'll take even longer to do so. And if you look at my accuracy then, oops, I want to look at the mean accuracy of my test data set, it's 0, right? We're doing really poorly right now. We're not getting anywhere close to correct. So if that's my training data set, well, I have no hope for my test data set. So again, you just kind of work through this and keep going at it. But if I need to do this a lot in order to get anywhere close to gaining accuracy, then we we have a problem here, right? We need to keep working on this. Oh, did I evaluate all of these things? Maybe I hope I did. It's here. Yeah. So the mean accuracy, yeah, we're still stuck at 0. So I could, add a for loop here, but I'm kind of constrained by the computational complexity here, right? This is taking a while to do. Each iteration over my data set is taking a little bit of a while. So how do I improve that? Well, one way of doing it is by what's called batching. And this is where I was talking about what you can do, in improving these things. Flux has a tool called flux.batch all my x's. I can batch together my x's, and that will, take all of my 5,000 examples, right? So look at what x's was. X's had been, this 5,000 element array of arrays. If I batch them all together, I end up with a matrix. Now, the cool thing about this matrix is that, again, this fits in with matrix multiplication. When I have a single x value that I pass into my model. So for example, I can call my model of my x's of 1, right? And that gives me a bunch of answers here that I can play with and see what the correct answer should be. So 0, 1, 2, 3, 4, 5. Sure enough, it's giving me the correct answer here, right? And it's telling me that that's right. And I can do flux.one cold of this, and sure enough, it's giving me 6. Oh, whoops, I need to do 0 through. Oh, maybe that's why I was seeing as accuracy of 0. I think I might have been missing this 0 through 9 here. So that's indeed giving me the correct answer. But now what would happen if I evaluated my model with 2 vectors at the same time, right? And I wanted to do a model of 1 through 2. Well, that's not going to work. I could do my model pointwise, which will give me 2 elements back, right? My first one and my second one. But what's kind of cool here is if I horizontally concatenate my x's together. So I have a vector of x's of 1 and a vector of x's of 2, put them together into a matrix and call my model on that matrix itself. Well, here's my output for that first vector, and here's my output for the second vector. This totally just falls out of doing a matrix multiplication. We can stack our inputs as multiple columns, and the model will happily give us multiple outputs at the same time. So now not only are we getting multiple answers for a single data point, but we're getting multiple answers for multiple data points all at the same time. And this is using matrix multiplication. And just as we saw an improvement in our computation time by moving from single data points, asking single questions of our model to asking 10 questions at once, we can similarly see a nice speed up by, instead of asking for single data points at a time, to asking about many data points at a time, and asking our model to evaluate whole matrices at a time. And so then this will get the loss function for not just one single data point, but potentially the entire data set. So I could evaluate my model on the entire data set by simply asking Flux to batch them all together. And I get all 5,000 answers rapidly and quickly back again. And so sure enough, you can see 5, 0, 4, 1, 9, and you get the answers that you would expect here. Let's just see if I get that mean accuracy. Oh, right. So I think my accuracy function here is incorrect. Yeah, that's the problem. I forgot to transition. I had updated my accuracy function on my command line, but hadn't updated it in my notebook. That's why I was getting 0% accuracy. So now you can look at, what is my mean accuracy of all my X's and all my Y's? Maybe, what am I doing wrong? So that's false. Oh, did I actually evaluate that? Maybe I didn't evaluate that. I copied it, pasted it. There we go. Sorry about that. So now you can see my mean accuracy of my test data set is already at 95% of, if I do the same thing with the mean accuracy of my test data set, we're at 90%. So training 95, test 90, and get that going. Let's see what happened here. Okay. So that is our accuracy. And we could continue training this. But what I was talking about was, improving the performance here, right? So I want to improve the performance. So instead of training on, looping over, 5,000 examples, sorry about that. Doing some development work at the same time. So, timing this over the data set as it takes about 0.7 seconds. If I were to instead use flux.batch all my x's together, flux.batch all my y's together, right? And those are my 2 data points, and put them in and pass them directly. That will go through and do them all at once. The first time we do that, it'll compile it. The second time, we see a factor of 10 or greater improvement in our performance here. So that is a huge impact on how you can improve things by batching your data together. Again, it's just now I'm taking my entire data set at once. And you can improve things even better by tuning your batch sizes. So I might not want to go through the entire data set. I might want to limit it to fit in my RAM nicely, or potentially to run on a GPU machine. And now we're talking about matrix multiplications, which is where GPUs really shine. And so now I can jump over to improve this even farther by putting my data and my model onto a GPU, and Flux will happily train it there and compile efficient kernels to do the training on a GPU device instead of on my desktop. And you'll see another factor of 20 or so improvement with typical modern GPUs. And so that will really get my training loop down in no time at all. So I can continue to improve this. You'll still see, oops, I don't want to do that one. I'm going to do my training of my batched version. You'll still see, some limits to how well I can train my model here because of my network itself, right? Because of the way that I'm using my features. And this gets to kind of that feature question that we were talking about earlier, where, I'm treating each and every single pixel as a, single value. So now I'm up to about 97% accuracy on my my training data set, but I'm stuck around 91% accuracy on my test data set. And this is about as good as you'll see with this kind of network diagram, this kind of neural network. And the reason for that is simply because I'm destroying a good amount of the image that I have, right? So remember what our images look like. We have images of 1 is this 5, right? This is what things look like. But by the time I pre-process it, I put it into a vector, which looks something like this instead. And I'm treating each and every single pixel as independent. And I'm saying, hey, if this particular pixel is hot, then we want to interpret that as some way. Well, that's not how you and I look at this 5 and see things. We don't have a particular meaning for this one pixel right here. What we have instead is we have some meaning to the shape or the connected regions of this image. And so that's where we want to move towards a more complicated, a more robust way of looking at this. The way to do that is to move towards, you want to move towards what's called a convolutional neural network, where instead of vectorizing my image and flattening it out into a single splotch of zeros and ones and things in between, we want to look at 3x3 grids, for example, or 5x5 grids of our image itself, and iterate over it and allow our neural network to choose what weights should be important. So this allows our neural networks to, instead of seeing single pixels, they'll look for patterns in our image. And this is really where modern machine learning has taken off, is the ability to have these more complicated neural network structures, like convolutional neural networks. And the way you do that in Flux is quite simply, let's go to fluxml.ai, the experiments tab. So we can go in, look at this MNIST classifier. This is now what we've trained, right? And you can actually, I have a demo that y'all can check out later. I know we're getting towards the end of the course, that actually trains this and gets it going using just 10 minutes of cloud compute on a GPU that costs about $1. And it's pretty easy to get running. So this is how you can do it. But to see the code here, you now know enough about Flux to gain the basic principles. And so this is the code for a convolutional neural network. We have a little bit of a function here that batches together groups into what are called mini batches. So instead of one giant batch of our entire data set at once, we're going to have smaller batches that fit into our GPU well. We have a get processed data that simply grabs, remember, our MNIST.labels, our MNIST.images, partitions them into mini batches. So we have a bunch of mini batches that will do, say 100 at a time, for example. And then we build our model. And what does our model look like? Well, it's a chain, right? It's a chain. It's a Flux chain of a bunch of networks that just iteratively call each other. And the tricky part is, getting your dimensionalities correct. So we keep a 28 by 28 image because we want to do a convolution on the image itself. We don't want to vectorize it. So we pass in a 4-dimensional array here. That's the only tricky part. And we end up, with 16 different varieties of convolutions of 3x3 grids that we go through. We do a pooling operation that's simply taking the max of a 2x2 grid, looking at the max of each value there, and reducing our image in half. So instead of 28 by 28, we get 14 by 14, and so on and so forth. And then at the final output stage, we have a dense neural network that takes the, whatever the output here was, so 7 by 7 times however many, 32. So it's going to be, 3 by 3 by 32. You can end up with your total output size and 10 outputs. So this is, just a deep neural network with 1, 2, 3 convolutional layers, 1, 2, 3 pooling layers that don't have any parameters to train. They just take a maximum. A flattening layer, again, doesn't have any layers or any tunable parameters, just flattens it out into a vector. And then a product of all of our outputs. So then how would you do this on a GPU? Well, it's as simple as calling the GPU function on our training set or testing set and the model itself. This is how you communicate to Julia using the CUDA package, which was loaded at the top here, that says, hey, if I have a GPU, let's move these things onto it and move them there so that way you can get them going. And then you can make sure that the model is precompiled and running, and you go through your training loop. And your training loop, again, it's what you know. You've done this, you've seen this, you're training it. We have our loss function, take the parameters of our model over our training set with our optimizer. It doesn't look any different, right? If it's on GPU or on a CPU, it just works the same way. This is kind of the beauty of Flux. and goes through here, calculates again the accuracy against the test set. So that way you can see if your accuracy hits 99.9%. That's the kind of performance that you can see. And then you end up saving your outputs, and then you can introspect it. So I know we're running late on time. I'm happy to stick around for about 10 more minutes to answer any questions or potentially show how you would do this in a real world example, and how you'd actually train this and get it going. And then how you could build a Julia dashboard to play with it and rebuild that example if folks are interested. But thank you all for your time. I know this has been kind of a whirlwind tour of going through these things, but hopefully now you've made your way from understanding the basics to knowing how to do it in Flux. And remember, the core understanding here is these 5 lines of code, right? You define your model, and how you define it, up to you. You test it out, see what works, see what's computationally efficient, what's tractable. You have your loss function. Your accuracy function can help you make business decisions, figure out, loss is the machine learning decision, accuracy is the business decision. Your optimizer, your data, and your training loop. And that's it. That's how we do this. And the rest is that art form of getting things going. So best of luck to all of you as you go through your machine learning career and have fun. Really, that's the key thing. Try things out, see how it works. The cool thing here is that it's imminently explorable, right? You can just keep testing things out. It's very, very hackable, very tractable to play around with things, try different activation functions, see what happens. I encourage you to go back to those smaller examples too and watch what happens as you change network sizes, as you change activation functions, see what's going on there. And it can be a fun little interactive playground for you to work with. So thanks everyone, you're free to go. And like I said, I'll stick around for maybe 10 more minutes if there are any questions. And if not, if folks are interested, I can demonstrate how you would get this, this example running on GPUs in the cloud using cloud compute resources as kind of a little Julia computing advertisement if you're interested for the last 10 minutes on how to run this on Julia Hub.
Thank you, Matt. That was great.
Thanks for sticking around, and thanks for being a part of this. How are folks feeling? Folks have energy for 10 more minutes here to see what a GPU example would look like?
Yeah, absolutely, Matt. I'm looking forward to that. Yeah, I'm here.
Okay, cool. That's all I need. One person is great. This is the end of my Friday afternoon after a very busy week, so I have nothing else on my plate. And as soon as I'm done here, I'm done for the week. So happy to stick around for just a little bit more. Yeah. Okay, so let's open up. I have a notebook here. Let's open an example that I've been working with. That you all can follow along with. It's not in the training materials, but it is free and open source and on my Git repository. I'll save all of these things and close it. Okay, so on my GitHub here, I'll just go to github.com/mbauman. I have a repository that's called the MNIST demo repository. There we go. And I'll paste it in here. So this is a repository that I've been working on a little bit and making some fun little examples on using dashboards and deploying these things in the cloud. So let's go to, hey, thanks, Peter. Thanks for being a part, and thanks for your great questions. So I'm going to go back to Visual Studio. So I have this set up to train and test. And this is essentially that model that I had defined, that I grabbed from that TensorFlow exam, or the experiments example, right? So I just copied and pasted it. It goes through, makes all my mini batches, includes all these things, and we can kind of look and see what this looks like. So let me start up my REPL. And let's include my model here. So I've separated this out into a model definition file that will, if I have CUDA, so it uses the CUDA package here. If I have it, it'll say, hey, CUDA is here. I'm on my laptop though, which doesn't have a GPU. And it doesn't have that, so it'll just be a no-op. The CUDA package will happily load on computers, or should happily load. I know one of you, I forget, one of you were having difficulties loading the CUDA package on Windows, and I'm not sure what that is, but you should report it or send me the full stack trace, and I can work with the CUDA team to try to dig out what was going on there. So here I have this all set up. So now we can kind of introspect, what we have and how this works. So let's get our process data. And I just have this simple args structure to, define the setup here. And what I get back are all of my training set and my test set. So let's say train set, test set equals get process data. So my training set here is a bunch of mini batches, right? And set up in a way that, we can grab out the first mini batch, and that will give me a single data point, right? So we can say X comma Y. So X is my matrix of inputs, and they're stacked in a very particular way here. So I'm putting them together in batches of 128. So the stacking here is a little bit peculiar. It's a 4-dimensional array, and it outputs, each, the first 2 dimensions are my image itself, right? And so if I were to just using the images package, I think I might need to add it here if I'm going to play with this. Might as well. We can look and see what this structure looks like, because the convolutional neural network needs to have things in a particular structure in order to iterate over them and convolve these things and get them set up to work nicely. So, oh shucks, that's going to take a minute. Maybe I won't worry about that. You know what this thing looks like though, right? This is the black area around the outside. This is the 128th image on the inside, or if I go to the first one here, this is my 5 here. That's the hat of my 5, that's the tail of my 5, and in the middle is the interesting part. And it's 28 by 28, right? That's the dimensions of my image by 1. So I have 1 color channel, you can think of it as, right? It's just a grayscale image by 128 batches. And Flux is built to work on these things in this manner for its convolutional neural networks in batches like this. And it knows how to iterate over these very efficiently with matrix multiplications, which again, is at the core of a convolution as well. So I can go in here and let's build my model. So I can go in here and let's build my model. Whoops, I need to define args. Args, like that. So now I have a model that is, again, it's just a chain, right? And I can look at what that model does to an individual image, and you can kind of watch this happen. And it's kind of cool to see what goes on. Yeah, maybe it is worth looking at the images here. But before I do that, I'm going to actually, I'll come back to that in just a second. Let me just do using images. That will take just a moment. So let's look at how this looks to deploy in the cloud while that's loading. So I have my, kind of entry point into running this and training it. So I have a training loop, I have a testing function, and then I have some outputs, and I can save my outputs and things like that. So with VS Code now, you can install what's called the Julia Hub extension. This is free to install. It's a public extension that anybody can install. It'll authenticate to juliahub.com. I'm actually authenticated to a development server here, but by default, it'll authenticate to juliahub.com and allow you to deploy your application in the cloud using compute resources that you spin up on demand and gets billed directly to you. We give you $25 of free compute. You can define kind of a cluster in the cloud to have as many cores as you want, as many nodes as you want. Of course, depending upon the size, the cost will change, and you can define this. This is, of course, a single core application, or a single machine application, I should say, that could run on CPUs, on a single core of a CPU. So I could use a simple, 2-core CPU machine that's very cheap. It's just 17 cents an hour, but it'll take a long time. It actually takes about an hour to run like this if I were to run it on a CPU machine. The cool thing is I actually have access to a GPU machine. I can use a beefy GPU, submit my job here, and hit start job. That'll connect to Julia Hub, bill it against my account that I have set up there, and spin up AWS workers that have GPUs attached to them and churn on my machine learning model as it goes. And so here you can see I've submitted this job, and it'll spin up a machine in the cloud and start working on this. While that's running, let's go back to my model and just kind of see what this looks like locally. So I've now loaded up my images data set, and we can go in and look at remember how I was looking at my training set. My first image of my training set is this 28 by 28 by 1 by 128 image. So of course I could grab just the first two dimensions, slice out the first kind of the page of this, batched together thing, and make it a grayscale image just by using the gray function from the images package. Oh man, need to add ImageMagick again. This is okay. So now I can, set up my image to, to output on VS Code here, and that'll just kind of show that number. I think it should be the number 5, right? That first image in my training set. Sure enough, there it is. Awesome. So we have my number 5. Now, if I had a trained model that I have my model that I've defined. This currently isn't trained, right? And if I were to run it on my laptop, it'd take about an hour to train. I don't want to do that. I want to not have to spend that time. But we can see what happens if I were to pass this train set, this first image, into my model, right? And I can pass this guy into my model. Just look at what does my model do to my first training set data here. Oops, what's going on here? Model of train set. Oh, I think I need to do, keep my dimensions there. Oh. Evaluate my model at my training set of 1. Oh, right. My training set includes both the X and the Y, right? So getting out to my first value of my training set, remember that my X's and my Y's are zipped together. So I want to get out the X value here. And of course, this model is not well trained, so it doesn't have a solid output, and it's kind of gibberish. The cool part is that I could introspect what happens after, the first layer, for example, and I can kind of see what the first layer cares about potentially, and look at, this model.chain, right, or the model.layers, and look into this first layer, this first convolutional layer, and watch what happens when I just run this first layer against my image, right? This first layer is itself a neural network. It's itself a flux function that I could call against my train set of one like this, and it'll output, what it does. And it actually has 16 outputs. And I could just look at, say how it, changes the image of the first example and the first output, and do a grayscale image of that. And this is how it gets transformed. And right now it's just gibberish. It's just noise. But I'm currently training it on the cloud, and eventually I'll be able to, once that training completes, I'll be able to download the results of that file, of the training loop, and get things going, get that loaded in. I already have one of those results file downloaded. It's this mnistconv.bson in my local directory. So I can jump ahead and load that up. So let's go here and go into my dashboard and look at it over here. So there's a function in Flux that loads in the parameters given a model and some saved data structure. And so I can load in the saved data structure, and it can update the parameters of my model based upon what was trained. And now I can do the same sort of game with my model and see, let's see where my plots go. There we go. So now you can see what the convolution here is. And this particular convolution is liking diagonals, right? It's liking the diagonals of my 5. It kind of highlights, you can think of the diagonal aspects of my 5, and it ignored the contra-diagonal aspects. And you can look at, maybe another layer. This one cares about that particular dimension, and so on and so forth. And so there are multiple different convolutions going on here, and you can kind of see how it's kind of gaining a more and more coarse representation of the image itself. And this is the output of that convolution. And so these are the trained weights. And now you can see how it's doing lots of fun things with the values of the weights, and kind of outputting some interesting rough shapes of like a kind of a more abstract representation of my model. And so you can follow this through. It's very visual, very fun to look at, and a lot of fun to play with. As this model is running, I can also go in here and look at the logs live as they're coming through. Let's see here. There we go. Hopefully we'll start seeing some of these log messages popping up. Sometimes it takes just a second to pull them up.
So, hey Matt, I got lost in a little bit in last point.
Yeah, sure.
So what do we download? So you trained the model there. What are you downloading? The results is BSON file. What does it have? It has a structure. What do you mean by structure?
It has the trained weights. So the model, remember, the model is just a bunch of layers that has, each layer, layer 1 is this guy here, is this conv layer. Layer 1 has a bunch of, weights and biases and things like that. We know what these layers look like for dense networks. Actually, let's pull out the output layer is model.layers of end, right? We can grab that last layer out. It's a 288 output layer with 10 things. We know what this one looks like, right? We've worked with these dense neural networks. It has a W matrix. It has a B vector. And so we can store these values, these weights and biases, these trained parameters of our network and load it in and save it out. And so in my model or in my training loop, I actually save here. Let me make this. This is my screen's getting a little bit cluttered. So as I'm going through here, I use BSON as a serialization format that's fairly robust and a nice option to use to save these things. It's a binary serialized object notation is what it stands for. And it can just save out the parameters of our model. And so you can save the parameters of your model and load the parameters of your model, and Flux supports both of these things to allow you to kind of productionalize your model. That's what's happening here.
So you're telling me, okay, once the model is trained, I get this BSON, I can host it somewhere and I can start making prediction.
Yeah, absolutely. Right, exactly. So you just need to download it, store it, save it, and load it up. And then it's very efficient to make the predictions once you're done. Let's see if I'm at my training loop here. Oh, nope, I'm still installing my packages. So Julia Hub will install the packages you need to get this going. It'll take some time to get this installed. Yeah, it just then, eventually what it'll have as its output is this results button that will download that BSON file. And so that's the way that this works. It just takes a moment to run. And I think in total, it takes about 15 minutes. So we don't have to sit here and watch this happen. I have some videos online that shows how this works. But it's a lot of fun to play with. And really at the end of the day, it's going to cost me $1 to run this job because it only takes 15 minutes on a GPU to run, which is pretty cool, I think.
What is the typical file size or what you download is BSON files? Like
That's a
MBs
good
or?
question. Yeah, so you can just kind of look at, so we have the params of my model, right, is all of the layers. And in this model, you can look at, the length of all of the lengths here and just take the sum of these guys. So in total, my model has 16,000 or 17,000 weights in it that it's trained. And it just kind of boggles my mind that I'm able to get good answers for all 17,000 of these, or enough of these that I get good predictions. And that's pretty cool in my mind. Then to see, how big that is, you can just, look in my local directory here. Here it is saved. It's 67K. It's pretty small. So, it's just saving the raw floating point values of 17,000 values, which really is very, very tiny.
Yeah, this is cool. I really appreciate you showing this to us. So point is like, so my training and prediction, these could be two separate
oh, definitely.
processes.
Yes.
Yeah.
I would separate those out. Yeah.
Correct. Yeah. So like, we have lots of sales data or purchase order data. So we can have content. We have 1, 2, or 3 machines just doing the training. And at the same time, I have like 10,000 people who want to use that data.
Right.
So our users, business users, they are not interested to see how the training works. They just want to see the prediction or end results. So.
Right, exactly. And importantly, the prediction is very cheap, right? I'm on my laptop here, not a GPU machine, timing how long it takes to evaluate the model, at this, first thing. It takes, very little time to evaluate 128 at the same time, 128 examples at the same time. And this is really cheap, especially compared to the training time. So you can deploy these out and have that's how, in fact, the experiments tab works on FluxML. Is that this is a trained model that's loaded into your JavaScript environment. And so it's actually not running Julia. It's just doing the evaluation in JavaScript using those trained models. And this is, exactly what's happening.
Cool. So this is using some kind of BSON file and making prediction, taking inputs from here. That's so cool.
Yep.
Yeah.
Yep. And then in my local directory here, I actually have a dashboard that, if I include dash.jl, it will load these files locally, put it together using the just released dash.jl for Julia. It's Plotly is a really awesome open source company that does really cool visualizations, and they have this dashboarding tool called dash.jl. That allows you to put together websites that actually run Julia, and don't do it in JavaScript, but rather do it in Julia. So I can go to localhost now. This is locally serving on my own machine that has this is the model that I trained in the cloud that's loaded here, and it does exactly the same thing. But now this is actually what I've trained, what I've played with, what you just saw, all the introspection here. This is that Dash experiments, and it's a lot of fun to play with. This is how this works. So we have a webinar that we just published on Wednesday that I kind of talk about the nuts and bolts of developing this application, in addition to deploying the model itself.
Can you please send me the link? I'm really very interested.
Absolutely.
And this, you can host it in your premises, right? This whole Dash thing.
Yeah, and we're working to actually host these things on juliahub.com as well, as kind of a Julia computing thing. So let's see here. I think I can pull up the webinar in just a second. Oh, I want this one. Here we go. So I pasted the YouTube link in our chat that kind of talks about, it's a joint webinar between Plotly and us at Julia Computing, talks about the announcement of this, this dashboarding tool. And this is just kind of a cool little example. So here you can see, now we're actually running this and we're iterating, we have our epochs going. What's really fun is that in VS Code itself, I can actually plot my accuracy as time goes on. So let's zoom out a little bit here. And I can set this to be my epoch, this to be my accuracy. And you can see this is actually, oh shucks, I didn't catch it quite in time. It trains so fast once everything's loaded, that this actually is a live interactive graph that will, interactively update as my model is training. And so you can see here that we're getting 99.2% accuracy on our test data set, which is what we want, right? Before, with the definitions that I was using, I was only getting 90% accuracy. And the reason that I didn't show you this interactively is because it's simply intractable to demonstrate locally. You need a GPU machine in order to do it. And so that's where Julia Hub comes in, is providing that machine. I can then go in and download these results file. This results button will download this version that I just trained. I'm connected to an internal repository that's currently broken. But if you go to juliahub.com and you're logged in, you can actually see, I'll log in here, and you can see my previous runs that I've done, and download them. You can see here, these are the previous runs. You can look at the details of how these worked. So here you can see that this was that MNIST demo. I got 99.3% accuracy in just 180 seconds, and it cost me $1 to do this job. And then on here, this one actually works. I can click and download the results, and that downloads that trained BSON file. So this is how we see things going and how things are working. Thanks for sticking around for this little bit.
No, wonderful. Thank you, Matt. Wonderful session. I'm so glad that, and thanks for taking the time to, walk me through these steps.
Absolutely, that's the fun part. That's where I have fun, is the interactive part. I always enjoy, interacting with.
Hey, Matt, can I ask you? So you are computing, Julia Computing. Do you provide consulting services as well, or are you guys only into the teaching?
Some we try to kind of focus our consulting services on places where we see the ability to improve the ecosystem as a whole as well. And so, we don't, we're a little bit selective in the consulting services that we do, and we're trying to build more general purpose components that can be widely used. But yeah, please feel free to contact us, and we'd be happy to talk to you about how that would look, and potentially collaborate on the consulting or even hosting or dedicated compute kinds of workflow for you.
Sure, yeah, I'll send you some proposal. The reason I asked, I work for Kaiser. I don't know if you know about Kaiser Permanente.
Yeah.
So we have even, you have been working with them or not really, right?
We've talked with some folks from Kaiser Permanente, and I'm trying to remember who we talked to there. I've been on a call with people from Kaiser before.
So we have Google, Microsoft, S2O. The people are working with us, and this is difficult times. Everybody wants to do something, so they are working us for free because they want to contribute to pandemic. We are doing a lot of work, related to this COVID-19. A lot of things, a lot of new projects going on. So even, I was looking for some help. Okay, definitely I'll get in touch with you. I'll send you some proposal. If you guys are interested, let's take it forward. Okay,
that'd be awesome. Yeah, I'll look forward to that.
Sure. I'll drop you an email, Matt. Okay. So I don't want to keep you any longer. I'll let you go. Okay. Thank you very much for this.
Thanks for the three of you for sticking around for this extra little time. I hope this has been helpful. Any other questions, Danica or Peter? Hopefully you've enjoyed this as much as I have. I've definitely enjoyed this lecture, and I want to work on incorporating more of this new stuff. This is brand new stuff that we've just been developing in the last 3 weeks or so, that I demoed in the last half hour here. So hopefully we'll work on figuring out ways of making this fit into the course a little bit more seamlessly, and give ourselves a little bit more time without going over like we did so far. Yeah. Thanks, and have a great weekend, everybody.
Thank you, Matt. Have a good weekend.
Yep.
Bye.
Take care.